Hello again, tired mind. Tonight, we journey through the story of optics, where ordinary sunlight is not really white at all. Isaac Newton split it with a glass prism and found every color hiding inside it. From ancient theories of light and vision to the invention of lenses, mirrors, and the first optical instruments that revealed hidden worlds, we'll trace how humanity learned to see. This tale unfolds alongside soothing music and abstract imagery, gently uncovering little-known wonders and fascinating stories to feed your curiosity as you drift towards sleep. So take a deep breath, sink into comfort, and let both mind and eyes rest as the story begins. The first light of dawn breaks over the eastern horizon, and a woman stands at the entrance of her shelter, watching. She has witnessed this transformation countless times, the gradual shift from darkness to light, the way shadows retreat and colors emerge from the gray pre-dawn world. Yet something about this daily miracle continues to hold her attention. What is this light that pushes back the night? Where does it come from, and where does it go when darkness returns? This moment of wonder, repeated across countless generations and civilizations, marks the beginning of humanity's long relationship with light. Our ancestors, lacking laboratories or instruments, possess something equally valuable: curiosity, patience, and the gift of careful observation. They watch the world around them with an attention we can scarcely imagine today, noting patterns and asking questions that would echo through millennia. The sun commanded their attention first, naturally enough. It rose and set with comforting regularity, yet its path across the sky shifted with the seasons. In summer, it climbed high, casting short shadows at midday. In winter, it traced a lower arc, and shadows stretched long even when the sun stood at its highest point. Different cultures marked these changes, building monuments aligned to solstice, sunrises, or equinox sunsets, demonstrating that observation of light had become deliberate, purposeful, sacred. But light revealed itself in other ways too. Rainbows appeared after storms, arcing across the sky in bands of color that seemed to have no physical substance. You could not touch a rainbow or capture it, yet there it hung, vivid and real to the eye. What strange property of light created these colored bridges? Some cultures saw them as pathways for gods or spirits. Others recognized them as phenomena connected to both sun and rain, appearing only when these two conditions met. The questions accumulated. Was the rainbow somehow in the water droplets? In the sunlight? In the space between earth and sky? At night, a different kind of light took over. Stars emerged, countless points of luminance scattered across the darkness. The moon waxed and waned, sometimes a thin crescent, sometimes a full disk bright enough to cast shadows of its own. Ancient observers noticed that moonlight seemed different from sunlight. Cooler, gentler, less revealing. They saw that the moon's light could be blocked by clouds just as the sun's could, but the moon itself changed shape across the month, while the sun remained constant. What was the relationship between these two great lights in the sky? Egyptian astronomers charted the stars with remarkable precision, creating calendars based on celestial movements. Chinese observers recorded solar eclipses, those startling moments when daylight failed and the sun appeared as a dark disk surrounded by a glowing halo. Babylonian scholars tracked the planets, those wandering lights that moved against the fixed backdrop of stars. All of this required careful watching, the patient accumulation of observations across years and generations. Closer to hand, there were other optical mysteries to contemplate. Still, water created perfect reflections, doubling the world in a way that seemed almost magical. The reflected image showed everything reversed, left becoming right, yet otherwise faithful to what it mirrored. If you disturbed the water, the reflection shattered into fragments and dancing light. When the water settled, the reflection returned. What was the nature of this phenomenon? Was the reflection somehow in the water? Or did the water merely reveal something about how light behaved? Polished metal offered similar reflections, more durable than those in water. Bronze mirrors became prized possessions in ancient civilizations, allowing people to see themselves clearly for the first time. The reflection in a mirror remained stable, unlike the easily disturbed water surface, yet it too showed that curious reversal. And the quality of the reflection depended on the quality of the polish. A rough metal surface scattered light in all directions, while a smooth one gave back clear images. Fire provided light of yet another kind, light that humans could create and control. A flame pushed back darkness, made the night navigable, extended the useful hours of the day. But firelight flickered and danced, casting moving shadows that behaved differently than the steady shadows of sunlight. People noticed that objects closer to a flame cast larger, softer-edged shadows, while the distant sun created sharper shadows that all ran parallel to one another. These observations hinted at geometric relationships, at rules governing how light traveled and interacted with objects. The human eye itself presented profound questions. How did seeing happen? When you looked at a distant mountain, something connected your eye to that faraway peak, allowing you to perceive its shape and color. But what was that something? Did the eye reach out to touch what it saw, sending forth some invisible extension of itself? Or did objects somehow send their images to the eye? The answer was not obvious, and thoughtful people could argue persuasively for different explanations. Some noticed that eyes seemed to gleam in certain lights, as when animal eyes reflected firelight from the darkness. This gleaming suggested that eyes might emit something, might be sources of vision rather than passive receivers. Yet eyes could also be damaged or blinded, could fail with age or injury, which suggested they were receivers of something external rather than generators of sight. Ancient physicians in Egypt, India, and Greece studied the anatomy of the eye as best they could, recognizing structures within it, the clear outer portion, the colored iris, the dark opening at the center. They could see that this opening changed size, growing smaller in bright light and larger in darkness, as if regulating how much light entered. But the connection between these physical structures and the experience of sight remained mysterious. All these observations of sun and moon and stars, of reflection and shadow, of rainbow and flame, of the seeing eye, accumulated across centuries. They formed a foundation of questions and wonderings that would eventually demand more systematic investigation. Ancient peoples could not measure the speed of light or calculate angles of refraction, but they could watch carefully, remember clearly, and ask persistently, what is light? How do we see? What are the rules governing these phenomena that so thoroughly shape our experience of the world? These questions, born under ancient skies and beside still pools of water, would eventually find their way into the hands of philosophers and mathematicians who would attempt to answer them through reason and geometry. The ancient Greeks possessed a quality that would shape their entire approach to understanding the world around them, an insatiable desire to know why. When they looked at light and vision, they did not simply accept that eyes could see. They needed to understand how this miracle occurred, and in their quest for answers, they developed theories that would influence human thought for more than 1,000 years. In the settlements scattered across the Greek peninsula and the Mediterranean shores, philosophers gathered students in shaded colonnades and sun-drenched courtyards to discuss the fundamental nature of reality. Among their most pressing questions was one that seems almost obvious to us now, yet proved remarkably difficult to answer. What happens when we see something? Pythagoras, the mathematician whose name we associate with triangles, proposed an intriguing idea in the 6th century before the Common Era. He suggested that vision worked through a kind of fire that emanated from the eye itself. According to this view, our eyes were active participants in seeing, reaching out into the world with something like flames or rays that touched the objects we observed. When these visual rays made contact with an object, the information somehow traveled back to us, creating the experience of sight. It was an attractive theory in many ways, elegant in its simplicity, and it positioned human beings as active seekers of knowledge rather than passive receivers. This notion of the eye sending forth something into the world gained followers and variations. Empedocles, who lived in Sicily during the 5th century before the Common Era, developed a more elaborate version of this fire theory. He believed that the goddess Aphrodite had created the human eye by kindling a fire within it, protected by delicate membranes that allowed the inner fire to shine forth. In his poetic way of explaining natural phenomena, Empedocles compared the eye to a lantern. Just as a lantern's flame shines through protective glass or horn panels to illuminate the darkness while being shielded from wind and rain, the eye's inner fire projected outward through its protective coverings. This internal flame, meeting with the external light of day, enabled vision to occur through their combination. The great philosopher Plato, whose academy in Athens became a center of learning that endured for centuries, further refined these ideas in the 4th century before the Common Era. His theory incorporated both the fire from within the eye and the light from outside. He proposed that a gentle fire flowed from the eye and merged with daylight. This blended stream then interacted with objects in the world, and through this interaction, visual information returned to the soul. For Plato, vision was a complex cooperation between the internal fire of the eye, the external light of the sun, and the soul's capacity to interpret what it received. It was characteristic of his thinking that he saw vision not as a simple mechanical process, but as something involving multiple elements working in harmony. Yet not all Greek thinkers agreed with this emission theory of vision. Aristotle, who had studied at Plato's academy, but developed his own distinct philosophical approach, took a contrary position. With his characteristic attention to practical observation, and logical analysis, Aristotle argued that the eye could not possibly send out rays to touch everything we see. He posed questions that highlighted the weaknesses in the emission theory. If our eyes truly sent forth something to create vision, why could we not see in complete darkness? Why did vision require external light to function? And how could we instantly see the distant stars the moment we opened our eyes at night? If vision required our eyes to send something across that vast distance, surely there would be some delay. Instead, Aristotle proposed that objects themselves were responsible for initiating vision. He suggested that illuminated objects affected the transparent medium between them and the eye, usually air or water. This medium, when activated by light, carried information about the object's color and form to the eye. In this view, the eye was a receiver rather than a projector, responding to changes in the medium caused by visible objects. The eye, he believed, contained water that was capable of being affected by these changes, allowing us to perceive the world around us. Aristotle's student Theophrastus explored these ideas further, considering how distance and medium affected vision, and pondering why objects appeared different when viewed through water or other transparent materials. The questions multiplied, each answer revealing new puzzles to solve. These competing theories represented more than mere speculation. They reflected different philosophical approaches to understanding reality itself. The emission theories aligned with views that emphasized the active, outward-reaching nature of human consciousness and the special status of humans in the cosmos. The theories that made the eye a receiver fit better with more mechanistic explanations of how the senses worked and how information flowed from the world into our mind. What remains striking when we consider these ancient debates is how seriously the Greeks took the problem of vision. They recognized that sight was neither simple nor self-explanatory. They understood that the experience of seeing required explanation, that there must be some mechanism or process that allowed images of the world to enter our awareness. Their willingness to propose theories, debate them rigorously, and seek logical consistency marked a profound shift in human thinking. The Greek approach established something crucial for the future of optics: the conviction that vision could be understood through reason and systematic thought. They created a vocabulary for discussing these problems and established that natural phenomena, even something as seemingly magical as sight, were proper subjects for philosophical investigation and logical analysis. Even when their specific theories proved incorrect, their insistence that vision required explanation and their methods of logical argumentation created fertile ground for future discoveries. As twilight settled over the Aegean and philosophers concluded their daily discussions, returning to their homes through narrow streets lit by oil lamps and starlight, they carried with them questions that would echo through the centuries. The debates between emission and reception theories would continue long after the classical Greek period ended. These questions about light and vision, first articulated so clearly by thinkers in togas and sandals, would travel through time and across cultures, waiting for new minds to reconsider them with fresh approaches, and eventually new tools for investigation. The foundation had been laid. The questions were posed. The philosophical frameworks were established. The story of optics would now begin its long journey through other lands and other centuries, carrying with it the Greek gift of systematic, rational inquiry into the nature of light and vision. In the bustling intellectual landscape of ancient Alexandria, where Greek thought flourished under the Egyptian sun, a mind of extraordinary precision turned its attention to the mysteries of sight. Around 300 BCE, perhaps within one of the great halls where scholars gathered to debate and discover, Euclid began to organize the scattered observations about vision into something remarkable, a systematic mathematical framework. Euclid was already becoming known for his methodical approach to geometry, that elegant discipline of points, lines, and planes. But his interest extended beyond abstract shapes drawn in sand or scratched onto wax tablets. He wondered whether the same logical principles that govern triangles and circles might also explain how we see the world around us. This question would lead him to compose a treatise he called Optics, a work that would influence how humanity thought about vision for nearly 2,000 years. The foundation of Euclid's approach rested on a series of simple assumptions, stated clearly at the beginning of his work. He proposed that vision occurs through straight lines extending from the eye to the object being viewed. These visual rays, as he conceived them, traveled outward in perfectly straight paths, forming a cone with its apex at the eye, and its base spreading outward to encompass whatever lay in the field of view. It was a geometrically beautiful idea, one that could be drawn, measured, and analyzed using the tools of mathematics. Working with this framework, Euclid began to explain phenomena that had puzzled observers for generations. Why do distant objects appear smaller? Using his geometric rays, he could demonstrate that the angle formed by the visual cone becomes narrower for objects farther away. Two people of identical height, one standing near and one far off, would subtend different angles at the eye, creating the impression of different sizes. The explanation emerged naturally from the geometry, as inevitable as the properties of triangles. He explored the question of why we cannot see all parts of a sphere simultaneously, showing through careful geometric reasoning that the visual rays could only reach a certain portion of any curved surface. He investigated why parallel lines appear to converge in the distance, anticipating principles that Renaissance artists would later formalize as perspective. Each observation became a proposition, each proposition supported by logical demonstration. Euclid's treatment of mirrors revealed the true power of his geometric method. When light reflects from a polished surface, it follows predictable patterns that can be traced with straight lines and angles. He demonstrated that the angle at which a visual ray strikes a mirror equals the angle at which it reflects, a principle now known as the law of reflection. Though his work assumed rays traveled from the eye outward rather than into it, the geometric relationships he described remained valid regardless of the direction of travel. The elegant simplicity of this approach must have been deeply satisfying to those who studied it. Here was a vision reduced to lines and angles, phenomena of the eye transformed into diagrams that could be analyzed with the same tools used to understand circles and polygons. In a world where so much remained mysterious and unexplainable, Euclid offered certainty through geometry. His work on perspective proved particularly influential. By analyzing how visual rays spread outward from the eye, Euclid could explain why nearby objects block our view of more distant ones along the same line of sight. He explored how the apparent size of objects changes with distance according to mathematical principles. These insights would echo through centuries, informing not only natural philosophers, but also architects and artists seeking to represent three-dimensional space on flat surfaces. Yet for all its mathematical sophistication, Euclid's optics remained rooted in a fundamental misconception about the direction in which vision operated. Like many Greek thinkers of his era, he maintained that something must emanate from the eye itself to make vision possible. The alternative seemed difficult to imagine. If objects constantly sent out something in all directions, how could this avoid becoming a chaotic jumble? How would the eye receive a coherent image? The geometric elegance of rays extending outward from the viewer appeared to solve these problems. This incorrect assumption about vision's direction did not prevent Euclid's geometric principles from proving useful and accurate in many applications. The mathematics of reflection worked whether one imagined rays going out from the eye or light entering it. The relationships between angles, distances, and apparent sizes remained constant. In this way, Euclid had discovered genuine geometric truths about vision while embedding them in a theory that later generations would need to revise. The influence of his approach extended far beyond his own time. Medieval Islamic scholars would study and expand upon his work, translating it into Arabic and adding their own insights. European thinkers encountering these translations centuries later would find in Euclid's geometric method a powerful tool for analyzing optical phenomena. Even as the theory of outward projecting rays eventually gave way to more accurate models, the mathematical framework persisted. What Euclid had accomplished was the demonstration that human vision, mysterious as it seemed, could be approached through systematic reasoning and geometric analysis. He showed that mathematical thinking could illuminate aspects of nature that appeared at first to belong solely to the realm of philosophy or speculation. The eye, that window through which we experience the world, could be understood at least in part through lines drawn in the dust, through angles measured and relationships proven. As evening descended on Alexandria's harbors and libraries, as lamps were lit in the gathering darkness, Euclid's geometric rays offered a kind of intellectual light. They suggested that the universe operated according to principles that human reason could grasp, that the tools of mathematics could reveal patterns hidden within everyday experience. Vision might remain mysterious in many ways, but it was no longer entirely beyond understanding. The legacy of this systematic approach would ripple forward through time, influencing countless investigators who sought to understand how light and sight work together to reveal the world. Euclid had taken the first crucial steps toward treating optics as a mathematical science, complete with axioms, propositions, and logical demonstrations. In the quiet of night, that achievement resonates still. The great lighthouse of Alexandria stood as a beacon over the harbor, its fire visible for miles across the Mediterranean waters. But within the city itself, in the famous library and museum complex, another kind of illumination was taking place. Here, in the 2nd century of the Common Era, a scholar named Claudius Ptolemy was conducting experiments with light that would push the boundaries of understanding far beyond what Euclid had achieved with pure geometry alone. Ptolemy was already renowned for his astronomical observations and mathematical treatises, works that would influence scientific thinking for more than 1,000 years. Yet he also turned his considerable intellect toward the behavior of light itself, particularly the curious phenomenon that occurred when light passed from one transparent substance into another. The Greeks had long observed that objects viewed through water appeared displaced from their actual positions. A straight stick, partially submerged in a pool, seemed to bend at the water's surface. Stars observed through the atmosphere appeared appeared slightly shifted from their true locations. This bending of light, which we now call refraction, fascinated Ptolemy deeply. Unlike the purely theoretical approach of earlier philosophers, Ptolemy designed actual experiments to measure refraction with precision. He constructed careful apparatus to observe exactly how much light bent when passing between air and water, between air and glass, and between water and glass. Using a disc marked with angular measurements, he could position a light source at various angles and measure where the refracted ray emerged on the other side of the interface. These were not casual observations, but systematic investigations, with measurements recorded in tables showing the relationship between the angle at which light entered a substance and the angle at which it traveled through that substance. The apparatus itself was elegant in its simplicity. Ptolemy used a bronze disc with degree markings around its circumference, which could be positioned vertically. The disc could be partially submerged in water or have glass placed against it. By sighting along the disc's edge and marking where light appeared to come from after passing through the transparent material, he could determine the precise angles involved. Night after night, measurement after measurement, he built up tables of data showing how refraction behaved under different conditions. What Ptolemy discovered was that refraction followed regular patterns. The amount of bending depended on both the angle at which light struck the boundary between substances and the nature of the materials themselves. Light passing from air into water bent one way, while light passing from water back into air bent differently. Though he did not arrive at the precise mathematical law that would be discovered many centuries later, his systematic measurements represented something profoundly new in the study of optics. This was knowledge gained not through reasoning about the nature of vision or the geometry of rays, but through careful, repeatable observation of light's actual behavior. Ptolemy also conducted extensive investigations into reflection, building upon the geometric principles Euclid had established. Using polished metal mirrors of various shapes, both flat and curved, he examined how images formed and how light bounced from reflective surfaces. His experiments with curved mirrors revealed that they could concentrate light into focused points or spread it across wider areas depending on their shape. Concave mirrors, curving inward like a bowl, could gather parallel rays of sunlight into an intense spot of heat and light. Convex mirrors, bulging outward, spread reflections across a wider field of view. These investigations with mirrors were not merely abstract exercises. They had practical implications that the ancient world already appreciated. Burning mirrors that could concentrate sunlight to ignite fires were known and valued. The way mirrors distorted or clarified images had both practical applications and provided deeper insight into how vision itself worked. Ptolemy carefully documented the relationship between the position of an object, the curve of a mirror's surface, and the location where an observer would see the reflected image appear. The experimental approach Ptolemy embodied represented a subtle but significant shift in how knowledge about light could be acquired. Where earlier thinkers had relied primarily on logical reasoning and geometric proofs, Ptolemy demonstrated that systematic measurement and observation could reveal relationships that pure thought might miss. His tables of refraction angles, though not perfectly accurate by modern standards, showed that the natural world's behavior could be quantified and recorded. The patterns he detected hinted at underlying mathematical relationships waiting to be fully uncovered. Alexandria in Ptolemy's time was a cosmopolitan center where knowledge from many cultures mingled and merged. The great library housed texts from Greece, Egypt, and beyond. Scholars corresponded with thinkers across the known world. The museum provided support for investigation and contemplation. In this rich intellectual environment, the combination of geometric reasoning, astronomical observation, and experimental investigation created a fertile ground for advancing optical knowledge. Ptolemy's work exemplified how the ancient world at its height could move beyond speculation towards something approaching modern experimental science. Yet these achievements occurred within limitations that would eventually constrain further progress. The ancient world lacked certain tools and concepts that would prove essential for deeper understanding. Precision instruments remained crude by later standards. The mathematical frameworks needed to fully describe wave motion or to formulate exact laws of refraction had not yet been developed, and the philosophical assumptions about light and vision that dominated ancient thought, while productive in many ways, would eventually need to be overturned before optics could truly advance. Still, in those quiet hours in Alexandria, as Ptolemy adjusted his bronze disc and carefully noted his measurements by lamplight, experimental optics was being born. The questions Euclid had explored through geometry were now being investigated through direct interaction with light itself. Mirrors were not just objects for theoretical analysis, but tools for revealing how light actually behaved in the physical world. Refraction was not merely a curious effect to explain away, but a measurable phenomenon with discoverable patterns and regularities. The legacy of this experimental approach would endure, even as Alexandria's golden age faded, and the scrolls in its great library were eventually scattered and lost. The idea that light could be studied through systematic experimentation, that its behavior could be measured and quantified, that apparatus could be constructed to reveal its properties. These insights would be preserved and carried forward, waiting for future generations to build upon the foundation Ptolemy and his contemporaries had laid in that ancient city by the sea. As the knowledge of Alexandria settled into the libraries and minds of later generations, the torch of optical inquiry passed eastward, while much of Europe moved through centuries that would see classical learning fade into shadow. A different world was awakening to the possibilities of natural philosophy. In the great cities of the Islamic Golden Age, from Baghdad to Damascus, from Cairo to Cordoba, scholars gathered manuscripts, translated ancient wisdom, and began to ask their own questions about the nature of light and vision. The 9th century brought a remarkable flowering of learning across the Islamic world. In Baghdad, the House of Wisdom stood as a beacon of scholarship, its halls filled with the rustling of parchment and the murmur of debate. Here, translators worked with patient dedication to render Greek texts into Arabic, preserving works that might otherwise have been lost to time. The optical writings of Euclid and Ptolemy found new readers, scholars who approached these ancient ideas with fresh eyes and questioning minds. Among these scholars was a philosopher known as Al-Kindi, whose full name was Abu Yusuf Yaqub ibn Ishaq al-Kindi. Working in Baghdad during the 9th century, he turned his attention to the study of light with a vigor that would influence generations to come. Al-Kindi was not content merely to preserve the wisdom of the ancients. He sought to expand upon it, to test it, to understand it more deeply. In his writings on optics, Al-Kindi explored the fundamental nature of light rays, building upon the geometric approach that Euclid had pioneered centuries before. He carefully described how light travels in straight lines, spreading outward from luminous sources in all directions. This might seem obvious to us now, but in Al-Kindi's time, establishing such principles required careful observation and clear reasoning. He noted how light weakens with distance, growing dimmer as it spreads across greater space, and he contemplated the geometric laws that might govern this diminishment. Al-Kindi's work ranged across many aspects of optical science. He investigated the nature of shadows, observing how they formed when opaque objects interrupted the straight-line path of light. He studied the phenomena of reflection, considering how light bounces from polished surfaces according to predictable patterns. His writings showed a mind that moved comfortably between abstract theory and concrete observation, always seeking to understand the principles underlying what the eye perceives. The significance of Al-Kindi's work extended beyond his specific discoveries. He represented a broader movement within Islamic scholarship, an approach that valued both the wisdom of ancient authorities and the evidence of careful investigation. He wrote not just about optics, but about mathematics, music, philosophy, and medicine. His contemporaries knew him as the philosopher of the Arabs, a polymath whose curiosity seemed boundless. As the decades passed, other scholars joined this exploration of light and vision. The translation movement that had begun in Baghdad spread to other centers of learning throughout the Islamic world. Damascus became another crucial location where Greek scientific texts were preserved and studied. Scholars there continued the work of understanding how light behaved, how it interacted with different materials, how it could be measured and described mathematically. These medieval Islamic scholars did more than simply preserve ancient knowledge. They challenged it, refined it, and built upon it. Where the Greeks had often relied on philosophical reasoning and geometric abstraction, these later investigators began to place greater emphasis on direct observation and experimentation. They asked, what actually happens when light encounters a mirror? How exactly does light bend when passing from air into water? Can we measure these effects with precision? The work being done in these cities during the 9th and 10th centuries created an intellectual foundation that would prove crucial for later developments in optics. Scholars were establishing methods, refining questions, and developing a body of knowledge that combined the best of ancient wisdom with new insights born from careful study. They created an environment where asking questions about the natural world was not just permitted, but celebrated, where the pursuit of knowledge was seen as a worthy endeavor in itself. In the scriptoriums and libraries of the Islamic world, manuscripts accumulated. Works on optics sat beside texts on astronomy, mathematics, and medicine. Scholars could consult the writings of Ptolemy alongside commentaries by more recent thinkers. They could compare different explanations for the same phenomena, weighing evidence and reasoning. This accumulation of knowledge, this conversation across centuries and cultures, created the conditions for even greater breakthroughs to come. The peaceful rustle of pages turning, the scratch of reed pens on parchment, the quiet discussions between scholars in sunlit courtyards. These were the sounds of optical science advancing through the medieval period. In cities where different cultures met and mingled, where merchants brought not just spices and silk, but also ideas and questions. The study of light became part of a larger project of understanding the natural world. Al-Kindi and his fellow scholars could not have known how influential their work would become. They could not have foreseen that their careful preservation and expansion of optical knowledge would eventually flow back to Europe, helping to spark new investigations there. They worked because the questions themselves were compelling, because understanding how we see and how light behaves seemed a worthy pursuit for a human mind. As the 9th century gave way to the 10th, the stage was being set for an even more revolutionary approach to optics. The questions had been refined, the methods were being developed, and the ancient texts had been preserved and pondered. Somewhere in this world of scholarship and inquiry, a mind was forming that would transform optical science entirely, that would conduct experiments of unprecedented sophistication and develop theories that would stand for centuries. But that story would unfold in its own time, building upon the patient work of translation, preservation, and careful study that scholars like Al-Kindi had undertaken in the libraries and academies of the Islamic Golden Age. The turn of the first millennium brought with it a scholar whose careful observations would transform the understanding of light and vision forever. In the city of Basra, then later in Cairo, a mathematician named Abu Ali al-Hasan ibn al-Haytham pursued questions that had puzzled thinkers for centuries. Known in the Latin-speaking world as Alhazen, this Persian polymath would write what many consider the most important work on optics produced in over 1,000 years. Around the year 1011, Ibn al-Haytham completed his monumental Kitab al-Manazir, or Book of Optics, a 7-volume work that examined vision, light, and reflection with unprecedented rigor. Where earlier scholars had relied primarily on philosophical reasoning, he insisted on testing ideas through careful experiment. This marriage of mathematics and practical investigation marked a departure from the methods that had dominated for centuries. The question that most occupied his attention was one that had divided thinkers since ancient times. Did light travel from the eye to objects, or from objects to the eye? The emission theory, favored by many Greeks, proposed that vision occurred when rays shot forth from the eyes to touch the things we see. But Ibn al-Haytham recognized fundamental problems with this notion. How could the eye's rays instantly reach the distant stars the moment we open our eyes? How could something so small as the pupil generate enough rays to illuminate everything in our vast field of view? Through a series of elegant experiments, he demonstrated that light must enter the eye rather than emerge from it. He observed that looking at bright objects like the sun caused pain and left after images, surely a sign that something from the object was affecting the eye. He noted that we cannot see in complete darkness, no matter how much we might will our eyes to emit their supposed rays. The eye, he concluded, was a receiver of light, not its source. But Ibn al-Haytham went further, investigating exactly how light traveled from objects to our eyes. He worked in darkened rooms, carefully controlling the paths of light rays through small openings. These experiments with what would later be called the camera obscura revealed something remarkable. When light from an illuminated object passed through a tiny aperture into a dark chamber, it projected an inverted image on the opposite wall. The top of the object appeared at the bottom of the image, and the bottom appeared at the top. This phenomenon fascinated him deeply. He reasoned that light must travel in straight lines from every point on an object's surface. When these rays passed through the small opening, they crossed paths. Rays from the top traveling downward, rays from the bottom traveling upward, creating the inverted image. By making the hole smaller, the image became sharper, though dimmer. By enlarging it, more light entered, but the image grew less distinct. Through patient observation, he traced how individual rays of light behaved. He studied reflection, measuring the angles at which light bounced from polished surfaces. The angle at which light approached a mirror, he confirmed, always equaled the angle at which it departed, following precise geometric laws. He investigated refraction as well, examining how light bends when passing from air into water or glass, building upon the measurements made by Ptolemy centuries before. His experimental method was remarkably modern. Rather than simply contemplating light's behavior, he created controlled conditions to test specific ideas. He varied one element at a time: the size of an aperture, the angle of a ray, the distance from a light source, and carefully recorded what happened. He used his observations to challenge or confirm theoretical predictions, letting evidence guide his conclusions. Ibn al-Haytham also made detailed studies of the eye itself, examining its anatomy and proposing how its various parts contributed to vision. He described the eye's layers and humors, suggesting that the crystalline lens played a crucial role in focusing incoming light. While his anatomical understanding had limitations given the knowledge of his time, his recognition that the eye functioned as an optical instrument was profound. The Book of Optics addressed many phenomena that had puzzled earlier observers. Why do objects appear larger when viewed through certain transparent stones? How do mirrors create images that seem to exist in space behind their surfaces? Why does the moon appear larger near the horizon than high in the sky? For this last question, he proposed it was an illusion created by our perception rather than by refraction in the atmosphere, a psychological effect rather than a purely optical one. His work spread gradually through the medieval world. Copies of the Book of Optics made their way to scholars in other centers of learning. In the following centuries, it would be translated into Latin, eventually reaching European universities, where it would influence thinkers for generations. The thoroughness of his investigations and the clarity of his mathematical descriptions made his work an essential foundation for all who came after. What made Ibn al-Haytham's contribution so enduring was not just his specific discoveries, but his approach to understanding nature. He demonstrated that careful experiments could reveal truths that pure reasoning might miss. He showed that mathematics could describe the behavior of light with precision. He proved that patient observation of simple phenomena, light passing through holes, reflecting from surfaces, bending through water, could unlock deep insights about how the world worked. In the quiet of his study, surrounded by apertures and mirrors, polished metals and geometric diagrams, Ibn al-Haytham had done something remarkable. He had taken light itself, that ethereal, intangible presence that fills our waking hours, and shown it followed comprehensible rules. Vision was not magic or mystery, but a natural process that could be studied, measured, and understood. As scribes carefully copied his volumes and scholars absorbed his methods, the foundations were laid for a new way of investigating the visible world. The dark chamber with its inverted images would intrigue curious minds for centuries to come, eventually transforming into instruments that would capture reality itself. The light of understanding that Alhazen had kindled in his careful experiments with dark chambers and pinholes did not fade with the closing of his manuscripts. Instead, it grew brighter across the centuries, spreading through the hands and minds of those who would build upon his insights. The simple phenomenon he had observed of light passing through a small opening to project an image on the opposite wall would become one of the most elegant demonstrations of light's fundamental behavior, and a tool that would serve artists, astronomers, and philosophers for hundreds of years to come. In the quiet chambers where natural philosophers worked, away from the bustle of medieval streets and markets, the camera obscura began its gentle transformation from experimental curiosity to practical instrument. The name itself, meaning simply dark room in Latin, would not come into common use until much later, but the principle remained the same: a darkened space, sealed from all light except for a single small aperture, through which the outside world would paint itself in miniature upon the far wall, upside down and reversed, but perfectly recognizable. The beauty of this arrangement lay in its simplicity. No complex apparatus was required, no specially crafted lenses or mirrors. A room, darkness, and a hole, these were sufficient to demonstrate one of nature's most enchanting optical effects. Yet in this simplicity resided profound implications. The camera obscura proved beyond doubt that light traveled in straight lines from every point of an illuminated object. The inversion of the image showed clearly how rays crossing through the aperture carried information about the world into the chamber, creating a perfect correspondence between what existed outside and what appeared within. Scholars across the Islamic world, and eventually in medieval Europe, discovered Alhazen's writings and began to construct their own dark chambers. Some made permanent rooms with carefully positioned openings. Others experimented with portable versions, using boxes or tents that could be moved and positioned as needed. Each refinement brought new understanding. When the aperture was made smaller, the image became sharper but dimmer. When enlarged, brightness increased, but the image grew less distinct. There existed an optimal size, a sweet point where clarity and illumination balanced in harmony. The question of why the image appeared inverted puzzled many observers, though the geometry was not truly complex. Light reflected from the top of an object outside the chamber traveled in a straight line downward through the aperture to strike the lower portion of the opposite wall. Similarly, light from the bottom traveled upward through the opening to illuminate the upper part of the wall. The entire scene crossed through that single point, that crucial aperture, and in crossing, exchanged positions. What had been up became down. What had been left became right. The world turned inside out by the simple journey of light through a hole. Artists were perhaps the first to see the practical promise in this phenomenon. By the 13th and 14th centuries, painters, seeking ever greater realism in their representations of the visible world, found in the camera obscura a kind of truth-teller. The projected image showed precisely how objects diminished with distance, how parallel lines seemed to converge, how light and shadow fell upon three-dimensional forms. Here was nature itself, demonstrating the principles that artists labored to capture on panel and canvas. Some natural philosophers began experimenting with placing translucent materials, thin papers or scraped animal membranes, at the point where the image formed. This allowed the image to be viewed from the other side, restoring its orientation so that observers saw the scene right side up, though still reversed left to right. It was a small innovation, but one that made the camera obscura more practical for extended observation and study. The device found particular favor among those who studied the sun. Looking directly at that brilliant orb risked damaging the eye, a danger well known to ancient and medieval observers alike. But the camera obscura offered a safe alternative. By projecting the sun's image into a darkened room, scholars could observe sunspots, eclipses, and the sun's changing position throughout the seasons without endangering their vision. The sun became, through this method, not a blinding presence to be glimpsed and quickly looked away from, but a patient subject that could be studied at leisure on the wall of a dark chamber. In monasteries and universities, in the private studies of the curious, the camera obscura became a meditation on the nature of perception itself. What was the relationship between the image on the wall and the reality outside? How did this mechanical projection differ from, or resemble, what happened within the human eye? If a room with a hole could capture the world, might not the eye be, in some sense, a small camera obscura of its own? These questions would occupy some of the finest minds in the centuries to come, but already the parallel was being drawn, the connection suggested. The phenomenon also inspired a kind of wonder that transcended mere technical interest. Imagine sitting in darkness as afternoon light streams through a tiny opening, and there, on the white wall opposite, the world appears. Trees sway silently in projected wind. Clouds drift across an inverted sky. People walk past, unaware they are performing in miniature on your chamber wall, their every gesture captured in flowing light. There was something almost magical in it, though the magic was entirely natural, requiring no incantation beyond the laws of light's straight-line travel. As decades passed into centuries, refinements accumulated gradually. Some experimenters discovered that placing a convex lens over the aperture, rather than leaving it as a simple hole, could greatly improve the brightness and clarity of the image. This innovation would not become widespread until after the development of practical lenses for spectacles and other purposes. But once glassmaking advanced sufficiently, the lens-equipped camera obscura became a powerful tool indeed. The device also served astronomers who wished to map the heavens or track celestial movements with precision. By projecting the night sky into a darkened room, assuming sufficient darkness outside and sufficient brightness of the celestial objects observed, certain phenomena could be studied more easily than through direct observation. The steady image on a wall allowed for careful measurement and drawing, creating records that could be compared across nights and seasons. Through all these applications and refinements, the camera obscura remained fundamentally what Alhazen had first explored, a demonstration of light's geometric behavior. It was a tool of science, of art, and of contemplation. In its darkened space, observers could witness the world reformed in light, could see the straight path travel of illumination made visible and undeniable. The seeds planted by careful Islamic scholarship had germinated and were beginning to grow into something that would eventually help transform human understanding and capability. The camera Obscura stood ready, waiting for the next innovations that would come with improved glass and the mathematical understanding of how curved surfaces bend light to human purposes. The camera Obscura had shown medieval scholars something remarkable: that light itself could paint pictures, that the world could project its own image through nothing more than a small opening into darkness. But now, as the 13th century unfolded across Europe, minds began to turn toward a different question. What if glass itself, shaped and polished in particular ways, could transform vision? What if transparent materials could be coaxed into revealing what eyes alone could not see? In Oxford, where stone buildings rose grey against English skies, a Franciscan friar named Roger Bacon bent over manuscripts in the quiet hours. Born around 1219, Bacon possessed an unusual hunger for understanding the natural world through observation and experiment. While many scholars of his time devoted themselves exclusively to theological texts, Bacon studied everything he could find about light, vision, and the properties of transparent materials. He read Latin translations of works by Alhazen and other Islamic scholars, absorbing their insights about how light traveled and how it interacted with different substances. Bacon wrote extensively about what he called perspectiva, the science of optics that encompassed both the geometry of light rays and the nature of vision itself. But among his many observations, one particular fascination emerged: the strange and wonderful properties of curved, transparent materials. He noticed that when light passed through certain shapes of glass or crystal, something extraordinary happened. The world beyond appeared larger, closer, transformed. In his writings, Bacon described how a segment of a glass sphere, what we might call a plano-convex lens, could magnify the appearance of objects seen through it. He explained how such an instrument might prove useful for elderly persons whose sight had dimmed with age, allowing them to read letters that had become frustratingly small and indistinct. Here was a practical application of optical principles, a way that understanding light could serve human needs in everyday life. The friar went further, speculating with remarkable foresight about what properly crafted lenses might accomplish. He imagined that suitable arrangements of transparent materials could make small things appear large and distant things appear near. He wrote of the possibility of reading tiny letters from great distances, of seeing objects invisible to unaided eyes. These were not mere fantasies, but extrapolations based on what he had observed about how curved glass bent light according to predictable patterns. Bacon's writings circulated among European scholars through hand-copied manuscripts, spreading ideas about magnification and the manipulation of light. Yet he remained a figure of his time, constrained by the materials and techniques available in 13th century England. He could describe what might be possible, but the practical craft of grinding and polishing glass into precise optical shapes remained underdeveloped. The gap between theoretical understanding and practical achievement still yawned wide. During this same era, other European thinkers encountered optical knowledge flowing westward through translations. The great works of Islamic scholars, written in Arabic, were being rendered into Latin by translators working in places where Christian and Islamic worlds touched. In Spain, in Sicily, in the intellectual crossroads of the Mediterranean. These translations carried Alhazen's detailed experimental observations, Al-Kindi's theories about light rays, and the accumulated optical wisdom of centuries into European libraries and monasteries. The process was gradual and uneven. A manuscript might travel from Toledo to Paris, be copied by scribes, studied by scholars, and perhaps copied again. Knowledge moved at the pace of horses and ships, spreading through networks of correspondence, and the wandering paths of students moving between centers of learning. Each translation, each copying, each reading added to a growing European engagement with optical principles that had been thoroughly explored in the Islamic world during previous centuries. What makes this period particularly fascinating is how theoretical knowledge and practical craftsmanship began, slowly, to approach each other. Scholars like Bacon read about the properties of transparent materials and wrote about their potential uses. Meanwhile, in workshops across Europe, artisans worked with glass in increasingly sophisticated ways. Glassmakers in Venice perfected techniques for creating clearer, more uniform glass. Stonecutters and gem polishers developed skills in shaping hard, transparent materials into precise forms. These craftspeople rarely wrote treatises or theoretical works. Their knowledge lived in their hands, in the feel of the grinding wheel, in the judgment of which angle would produce the desired curve. They knew from direct experience that certain shapes of crystal or glass made things look bigger when placed over them. They understood, in practical terms, that didn't require mathematical formulation, that the degree of curvature affected the degree of magnification. The convergence of scholarly understanding and artisan skill would soon bear fruit in practical inventions that would change how humans experience the world. But in the 13th century, these streams of knowledge still flowed somewhat separately. Bacon could write eloquently about the potential of shaped glass, but he likely never created a truly effective magnifying instrument himself. Glassworkers could produce curved pieces that enlarged what lay beneath them, but they didn't necessarily understand the geometric principles that explained why this occurred. In monasteries and universities, in workshops and markets, the pieces were assembling. The ancient Greek geometry of light rays, refined by Islamic experimental methods, now resided in European libraries. The practical skills of glassmaking and polishing were advancing. The recognition that curved, transparent materials could alter vision was spreading beyond isolated observations into broader awareness. What remained was for someone to take the next crucial step, to deliberately craft a tool specifically designed to help failing human eyes see more clearly. As the 13th century drew toward its close, Europe stood on the threshold of an invention that would seem modest, but would prove revolutionary. The same optical principles that explained rainbows and reflections, that had led to the camera Obscura, would soon be applied to create something individuals could hold in their hands or wear upon their faces. The age of practical optical instruments for everyday use was about to dawn, emerging not from the studies of great philosophers, but from the practical workshops of craftsmen who shaped glass to serve human needs. The monks in medieval scriptoriums bent over their manuscripts with aging eyes, squinting at the careful letters they had copied for decades. Many found, as the years accumulated, that the words they once traced so clearly now blurred into indistinct shapes. The parchment seemed to recede from them, as if the very act of reading required distance the arm could no longer comfortably provide. In this practical difficulty lay the seed of an invention that would transform daily life more immediately than any theoretical breakthrough about light's nature. Somewhere in the monasteries and reading rooms of 12th century Europe, perhaps in several places independently, someone discovered that a segment of transparent crystal or glass, shaped with one side flat and the other gently curved, could be placed directly upon text to make it appear larger. These reading stones, as they came to be called, were hemispheres of beryl or quartz, polished smooth. When laid against parchment, they acted as primitive magnifying glasses, enlarging the letters beneath through the same principles of refraction that natural philosophers had pondered for centuries. Yet the craftsmen who shaped these stones likely gave little thought to theories of light bending as it passed from air into denser material. They simply knew that it worked. The reading stone required no understanding of why refraction occurred, only the recognition that curved, transparent materials could help failing eyes. A scholar would place the smooth stone over a line of text and move it slowly along, reading word by magnified word. The device was simple, requiring only a skilled hand to grind and polish the curved surface properly. Unlike the elaborate theories debated in universities, this was knowledge born in workshops, passed from artisan to apprentice through demonstration rather than written treatise. For more than a century, reading stones served those whose vision had dimmed with age, but they possessed an obvious limitation. One hand was occupied holding the stone against the page, moving it along each line. The reader's pace was slowed, and certain tasks became awkward or impossible when both hands were needed for other work. The natural question arose: could these helpful pieces of glass be suspended somehow before the eyes, leaving the hands free? The answer emerged in northern Italy during the final decades of the 13th century, probably in Venice or thereabouts, where glass makers had achieved particular skill in working their craft. Someone, whose name has been lost to history, realized that two reading stones could be mounted in frames and held before the eyes simultaneously. The earliest evidence suggests this breakthrough occurred around the year 1290, though the exact moment remains shrouded in the mists of time, like so many medieval innovations. These first spectacles consisted of two small convex lenses, each ground from glass or crystal, held in frames made of wood, bone, or metal. The frames were joined by a rivet that allowed them to be balanced on the bridge of the nose or held before the face by hand. Some early designs could be pinched onto the nose, while others required gripping. They were awkward by modern standards, yet revolutionary for those who used them. For the first time in human history, a person whose near vision had deteriorated could wear a device that continuously corrected their sight. The invention spread with remarkable speed across Europe. By the early 14th century, spectacles were being manufactured in various Italian cities and beyond. They appeared in paintings and manuscripts, perched on the noses of scholars and clerics. A portrait from 1352 shows Cardinal Hugh of Provence, wearing spectacles as he sits at his desk, the lenses clearly visible in their frames. Artists began including spectacles as symbols of learning and scholarship, visual shorthand for the studious contemplation of texts. The demand for spectacles created a new trade. Spectacle makers established shops and guilds, developing techniques for grinding lenses to different curvatures to help various degrees of vision impairment. The craft required patience and skill. The glass had to be shaped carefully to achieve the proper curve, then polished until transparent and clear. Variations in the glass itself, bubbles or impurities in the material, could ruin a lens or reduce its effectiveness. These early spectacles helped only with close work, magnifying nearby objects for those whose eyes had lost the ability to focus on near distances. The condition we now call presbyopia, which comes to nearly everyone with advancing years. The lenses were convex, thicker in the middle than at the edges, concentrating light to help the eye form clearer images of close objects. For those who struggled to see distant things clearly, no solution yet existed. That development would wait for future generations of lens makers to discover that concave lenses, thinner in the middle than at the edges, could address a different visual difficulty. The spectacle makers worked primarily through trial and refinement rather than optical theory. A customer would visit a maker's shop and try various lenses until finding a pair that helped. The maker would note which strength of lens suited which type of vision problem, building practical knowledge through accumulated experience. This empirical approach, grounded in what worked rather than why it worked, characterized much early lens making. Yet even without deep theoretical understanding, the spectacle makers were demonstrating something profound, that human vision could be augmented, that our natural limitations could be overcome through shaped glass. The eye, which philosophers and physicians had studied for centuries, could be helped by placing carefully crafted transparent materials before it. This practical success hinted at possibilities that would unfold over coming centuries. If glass could help the aging scholar read, might it also help us see things otherwise invisible, whether far away or exceedingly small? The monasteries and universities that had preserved and studied optical texts from antiquity now benefited directly from optical craft. Scholars who might have been forced to abandon their work as their vision failed could continue reading and writing into advanced age. The production and copying of manuscripts became possible for older scribes. Knowledge could be pursued longer, accumulated wisdom preserved, and passed forward by those whose eyes had been given this simple but transformative assistance. As the 14th century progressed, spectacles became more common, their design gradually refined. The frames improved, the glass quality increased, and the grinding techniques became more sophisticated. What began as a novel invention became an established tool, as familiar in its time as it remains in ours. The reading stone had evolved into something that could be worn, that became part of the reader rather than merely an instrument they held. In the workshops where artisans ground and polished these lenses, humanity was learning to shape light itself, bending it to our purposes, though we barely understood what light truly was. The craftsmen who had given the world spectacles in the workshops of northern Italy could scarcely have imagined where their practical invention would lead. As the 14th century gave way to the 15th, these reading lenses spread slowly across Europe, carried by travelers and traded among merchants. Yet even as this useful technology dispersed, something else was stirring in the Italian peninsula. A new way of seeing was emerging, one that would intertwine the study of light with the creation of beauty in ways that would reshape both art and science. In the studios and workshops of Florence, Milan, and Venice, painters were wrestling with an ancient problem. How could one represent the three-dimensional world upon a flat surface? How could depth, distance, and the solid reality of buildings and bodies be captured on wood panels and plastered walls? The answer they discovered lay in understanding the very nature of vision itself, the geometry of light rays that travel from objects to the eye. Artists had long observed that parallel lines appear to converge as they recede into the distance. Rails on a road, the edges of buildings, the furrows in a ploughed field all seem to meet at some far point on the horizon. In the early 15th century, the architect and engineer Filippo Brunelleschi conducted a remarkable demonstration in the streets of Florence. Standing at the door of the cathedral, he created a painting of the baptistry across the square, carefully calculating the precise angles and proportions according to mathematical principles. He drilled a small hole through the panel and invited viewers to look through it from behind while holding up a mirror. What they saw was astonishing. The painted image aligned so perfectly with the real building that the two seemed indistinguishable when the mirror was removed and replaced. This was linear perspective, a system that transformed painting from a craft of symbolic representation into something that could capture the optical truth of how we see. The principles were codified by Leon Battista Alberti in his treatise on painting, written in the 1430s. He described the picture plane as a window through which the artist views the world, with light rays traveling in straight lines from every point in the scene through this window to the eye. It was geometry made visible, Euclid's optical principles finding expression in pigment and gold leaf. But among all the artists and thinkers of the Renaissance, none pursued the study of light and vision with more passionate intensity than Leonardo da Vinci. Born in 1452 in the Tuscan hills, Leonardo filled thousands of pages with observations, sketches, and theories about everything he encountered. And light, that subtle phenomenon that made all vision possible, captivated him endlessly. In his notebooks, written in his characteristic mirror script from right to left, Leonardo sketched the anatomy of the eye with remarkable accuracy. He dissected animal eyes, carefully observing the spherical lens, the chambers filled with clear fluid, the network of what he called nerve-like structures. He understood that the eye was not simply a window, but an instrument, a device that transformed the light of the world into something the mind could comprehend. He drew diagrams showing how light from an object enters the pupil, noting the way the pupil contracts in bright light and expands in darkness, like the door to a room adjusting to control how much enters. Leonardo pondered deeply about how images form in the eye. He knew from the camera Obscura that light traveling through a small opening creates an inverted image. Yet we do not see the world upside down. He proposed various explanations, suggesting that perhaps the image inverted twice, once at the pupil and again before reaching the seat of consciousness. The true mechanism would await Johannes Kepler's work in the next century, but Leonardo's questions revealed a mind grappling seriously with optical reality. Beyond the eye itself, Leonardo studied light's behavior in the world. He observed shadows with the attention of both scientist and artist, noting how they blur at the edges, how they vary in darkness, depending on the distance from the object that cast them. He identified what he called primary light from the sun, or a flame, and secondary light reflected from illuminated surfaces. He noticed that a face looking out from a dark doorway is lit not only by the direct sunlight, but by the gentle glow bouncing from nearby walls and ground, filling the shadows with subtle color. Water fascinated him as an optical medium. He watched light bend as it passed from air into water, making submerged objects appear in different positions than they truly occupied. He observed the play of reflections on moving water, the way waves scatter light into shimmering patterns. He studied the rainbow, that ancient wonder, attempting to understand the geometry by which water droplets in the air transform sunlight into arcs of color. In his paintings, Leonardo applied his optical knowledge with extraordinary subtlety. His famous technique of sfumato, the soft blurring of edges and the delicate gradation of tones, arose from his understanding that the eye does not see perfectly sharp boundaries everywhere. Light scatters, air intervenes, and the living world appears to us with a gentle haziness that his contemporaries, with their crisper outlines, often overlooked. When we gaze at the enigmatic face in his portrait of Lisa Gherardini, the woman known as Mona Lisa, we are seeing paint applied according to optical principles. Layers of translucent glazes, creating the effect of light penetrating and reflecting from living skin. Leonardo was not alone in this fusion of art and optics. Albrecht Dürer in Germany created intricate diagrams showing devices for achieving correct perspective, mechanical aids that traced the geometry of sight. Artists across Europe were learning to observe light's effects with unprecedented attention. The highlights on fabric, the transparency of glass, the specific quality of illumination at different times of day. This artistic revolution occurred alongside and intertwined with what would become scientific optics, though the boundary between art and natural philosophy remained blurred. The Renaissance workshops were places of experimentation, where practical knowledge about materials, geometry, and vision accumulated. When a painter mixed pigments to capture the blue of a distant mountain, softened and lightened by intervening air, they were applying what Leonardo called aerial perspective, an optical phenomenon caused by light scattering in the atmosphere. The Renaissance thus bequeathed to the coming centuries not merely beautiful images, but a sharpened way of seeing, an attention to light's properties that would prove essential to the optical discoveries ahead. As spectacle makers continued their craft and scholars pondered ancient texts, the artists had demonstrated something crucial. That careful observation of light and vision, combined with mathematical understanding, could reveal truths about the world that casual glancing never would. The eye that Leonardo drew in his notebooks, that Alberti described in his Geometry of Perspective, was becoming understood not as a mystical organ, but as a device subject to nature's laws, an instrument waiting for the next generation of thinkers to fully comprehend its workings. The turning of the 17th century found Europe stirring with new questions about the nature of sight itself. While artists had mastered the representation of three-dimensional space on flat canvases, and spectacle makers had refined their craft of correcting vision, a fundamental puzzle remained unsolved. How did the human eye actually see? What happened inside that small, delicate organ to transform the light of the world into the vivid experience of vision? Into this landscape of wonder stepped Johannes Kepler, a man already celebrated for his revolutionary work on planetary motion. Born in the Holy Roman Empire in 1571, Kepler possessed a mind that moved fluidly between mathematics, astronomy, and the physical workings of nature. He had gazed through the darkness of night to discern the elliptical paths of planets, and now he turned that same penetrating curiosity inward toward the mechanism of seeing itself. In 1604, Kepler published his treatise on optics, a work that would transform understanding of the eye as completely as his laws would transform understanding of the heavens. But his journey to this revelation began with a practical problem. Kepler himself suffered from poor vision, afflicted with multiple eye conditions that gave him an intimate, personal stake in understanding how eyes worked. He knew firsthand the difference between clear sight and blurred perception, between the world seen sharply and the world seen through a veil. Kepler built upon foundations laid by others, particularly the insights of Ibn al-Haytham, whose book of optics had demonstrated that light travels from objects into the eye. But Kepler went further, asking the precise question that would unlock the mystery. What happens to that light once it enters? Where exactly does the image form inside the eye? The camera obscura provided his crucial insight. This darkened chamber, with its small opening, had fascinated natural philosophers for centuries, projecting inverted images of the bright world outside onto the opposite wall within. The similarity to the eye seemed obvious. Both were dark chambers receiving light through a small opening. But earlier thinkers had struggled with a troubling problem. The camera obscura produced an upside-down image. If the eye worked the same way, wouldn't we see the world inverted? Kepler made the bold leap that resolved this puzzle. Yes, he declared, the eye does work exactly like a camera obscura. Light enters through the pupil, passes through the clear lens, and projects an inverted image onto the back of the eye, onto the retina. The reason we don't perceive the world as upside down must have to do with how the mind interprets the image, not with how the eye receives it. The eye itself is simply an optical instrument, following the same geometric laws as any lens or curved mirror. This insight required Kepler to work out precisely how light bends when passing through the transparent structures of the eye. He devoted himself to understanding refraction, the bending of light as it passes from one material into another. Earlier investigators had measured refraction, noting that light changes direction when moving from air into water or glass. But Kepler sought to express these observations mathematically, to find the laws governing how much light would bend at different angles and through different materials. He experimented patiently, tracing rays of light through glass spheres and lenses, measuring angles and distances. He understood that the eye's lens must focus incoming light onto a precise point on the retina for vision to be clear. When this focusing failed, when the lens was malformed, or the eye too long or too short, vision blurred, and spectacles became necessary to correct the error. Kepler's work revealed the eye not as a mysterious, quasi-magical organ, but as a precision optical instrument, subject to mathematical description. The cornea and lens work together to refract incoming light, bending and focusing it. The pupil opened and closed to regulate how much light entered, like the adjustable aperture of a camera obscura. The retina served as the receiving surface where the optical image formed, ready to be transformed by nerves into the sensation we call sight. These insights emerged from Kepler's mind during years when he faced considerable hardship. His work on optics coincided with personal tragedies and the religious tensions sweeping through Central Europe. Yet through it all, he maintained his focus on understanding the natural world through careful observation and mathematical reasoning. His optical work received less immediate acclaim than his astronomical discoveries, but it proved equally foundational. Kepler also made crucial advances in understanding how lenses themselves worked. He systematically described how convex lenses converge light rays to a focal point, while concave lenses cause rays to diverge. He explained how combinations of lenses could magnify distant objects or make small things appear larger. These principles would prove essential for those who would soon construct telescopes and microscopes of unprecedented power. The implications of Kepler's work rippled outward through the scholarly world. If the eye was an optical instrument, then it could be understood, modeled, and even replicated or enhanced through clever arrangements of lenses. The boundary between the natural and the artificial, between the God-given organ of sight and the human-made tools of observation, became permeable in a new way. Kepler himself recognized that his work on the eye connected directly to questions about optical instruments. In later writings, he described how telescopes might be improved, how lenses of different shapes and combinations could extend human vision beyond its natural limits. He understood that once you grasped the mathematical principles governing light's behavior, you could design devices that bent and focused light according to your purposes. The quiet revolution in understanding, accomplished by Kepler's optical work, cannot be overstated. For thousands of years, vision had seemed immediate and direct, a mysterious connection between mind and world. Now it revealed itself as a chain of physical events. Light reflecting from objects, entering the eye, refracting through transparent structures, forming an inverted image, and finally, through processes still not fully understood, giving rise to conscious perception. This new understanding arrived at precisely the right moment in history. Within just a few years of Kepler's optical treatise, craftsmen in distant Holland would combine lenses in a tube and point their creation at the night sky. The theoretical understanding of how lenses and eyes worked would meet practical skill in lens grinding, and together they would unlock views of the cosmos that would astonish the world and challenge certainties held for millennia. The eye had been explained, and now it would be augmented, extended, and empowered in ways that would transform human knowledge itself. The year 1608 brought whispers of a remarkable invention from the Netherlands, where spectacle makers in the towns of Middelburg and Alkmaar had stumbled upon something extraordinary. By arranging two lenses in a tube, these craftsmen discovered they could make distant objects appear closer and larger. The exact circumstances remain somewhat unclear, though stories circulated about a spectacle maker's apprentice who noticed the effect while playing with lenses in the workshop. What began as an optical curiosity would soon transform humanity's understanding of the cosmos itself. Word of this spyglass, as it was initially called, spread rapidly across Europe. By the autumn of 1609, news of the device had reached Italy, where a mathematician and astronomer named Galileo Galilei worked at the University of Padua. Galileo had spent years studying motion and mathematics, building upon the optical understanding that Kepler had recently articulated about how lenses bend light according to predictable laws. When Galileo heard descriptions of the Dutch telescope, he immediately grasped the optical principles at work and set about constructing his own version. Working through the summer months of 1609, Galileo experimented with different combinations of lenses, seeking to improve upon the basic design. The Dutch instruments magnified objects only 3 or 4 times, which was impressive enough for viewing ships approaching harbour or observing distant landscapes. But Galileo envisioned something more powerful. He ground and polished his own lenses, testing convex and concave combinations, adjusting the distances between them within tubes of wood and leather. Through patient refinement, he achieved magnifications of 8 times, then 20 times, and eventually more than 30 times, far exceeding anything available elsewhere in Europe. The Venetian Senate recognized the strategic value of such an instrument for maritime navigation and military purposes. They invited Galileo to demonstrate his telescope from the top of the Campanile in Venice, where dignitaries peered through the tube and gasped at ships rendered visible far out at sea, long before they could be seen with unaided eyes. The Senate rewarded Galileo with a generous increase in salary and lifetime tenure at the university. But Galileo had already glimpsed a far more profound application for his optical instrument. On calm evenings in Padua, when his daily obligations were complete, Galileo turned his telescope skyward. The moon, which had always appeared as a smooth, luminous disk to the naked eye, revealed itself as something entirely different through his lenses. He observed a rugged surface marked with mountains and valleys, casting shadows that changed with the lunar phases. He measured these shadows and calculated that some lunar mountains must rise to considerable heights, comparable to Earth's own peaks. The moon was not a perfect celestial sphere, as ancient philosophy had insisted, but a world of terrain and topography, not fundamentally different from Earth itself. Night after night, through the winter of 1609 and into early 1610, Galileo methodically observed the heavens, sketching what he saw and recording his observations. He noticed that Venus exhibited phases like the moon, growing from crescent to gibbous as it moved in its orbit, a phenomenon that made sense only if Venus orbited the Sun rather than Earth. He observed that Saturn appeared oddly elongated, though his telescope lacked the power to resolve what later observers would recognize as rings. The Milky Way, that diffuse band of light crossing the night sky, dissolved under magnification into countless individual stars, far more numerous than anyone had imagined. Perhaps his most revolutionary discovery came in January 1610, when Galileo noticed 3 small stars near Jupiter, arranged in a line along the planet's equator. He almost dismissed them as background stars, but something prompted him to observe Jupiter again the following night. The stars had moved, but not in the way background stars should move. Over successive nights of observation, he realized these were not stars at all, but moons circling Jupiter itself. A 4th moon soon revealed itself. Here was direct evidence of celestial bodies orbiting a center other than Earth, a miniature planetary system playing out before his eyes. Galileo published these discoveries rapidly in a small book called Sidereus Nuncius, the Starry Messenger, in March 1610. The book circulated throughout Europe, creating both excitement and controversy. Here were observations that anyone with a sufficiently powerful telescope could verify. Yet they challenged long-held assumptions about the cosmos. The optical instrument had become a tool for discovery, revealing realities that existed beyond the reach of human vision alone. The telescope's impact extended far beyond Galileo's individual observations. Other astronomers began constructing their own instruments, each refinement in lens grinding and tube design bringing fainter and more distant objects into view. In Rome, Jesuit astronomers confirmed Galileo's discoveries, though debates about their interpretation would continue for decades. The German astronomer Simon Marius observed Jupiter's moons independently and proposed the names by which we still know them: Io, Europa, Ganymede, and Callisto. What made the telescope so revolutionary was not merely that it magnified distant objects, but that it revealed phenomena completely invisible to unaided human senses. For millennia, astronomers had observed the sky with only their eyes, aided by measuring instruments, but not by anything that gathered more light or resolved finer details. The telescope crossed a threshold, extending human perception into realms that had been forever hidden. It demonstrated that our senses, however carefully trained, might miss entire dimensions of reality that optical instruments could unveil. The technical challenges were considerable. Early telescopes produced images plagued by chromatic aberration, the rainbow fringes caused by different colors of light bending at slightly different angles through lenses. The tubes were difficult to aim and keep steady. Magnification often came at the cost of a very narrow field of view, making it challenging to locate and follow celestial objects. Yet despite these limitations, the telescope worked. It showed mountains on the moon and moons around Jupiter, facts that could not be unseen or ignored. As Galileo's observations became known, they raised profound questions about the reliability of human perception and the role of instruments in acquiring knowledge. Could one trust observations made through glass lenses? Or might the telescope create illusions? Some philosophers argued that instruments distorted reality rather than revealing it, but the consistency of observations, the ability of different observers using different telescopes to see the same phenomena, and the mathematical predictability of what was seen gradually established the telescope's credibility as a tool for discovering truth. The invention of the telescope marked a turning point in humanity's relationship with optical instruments. What had begun with simple reading stones and spectacles for correcting vision had evolved into devices that revealed entirely new worlds. As observers turned their telescopes toward different quarters of the sky, discovering sunspots, observing comets, and cataloging stars. it became clear that the universe contained far more than unaided eyes could ever perceive. The door had opened to distant worlds, and soon another optical instrument would open a door in the opposite direction, toward worlds equally hidden but infinitesimally small. As Galileo's telescope revealed the vastness of the cosmos, others wondered what secrets might lie hidden in the opposite direction, in the realm of the infinitesimally small. The same principles that magnified distant mountains of the moon could surely be turned toward the everyday world beneath our feet, toward the texture of fabric, the structure of an insect's wing, the mysterious composition of a drop of pond water. The compound microscope emerged from the workshops of Dutch spectacle makers in those same fertile years of the early 17th century. These craftsmen, already skilled in grinding lenses for eyeglasses and simple magnifiers, experimented with combining lenses in tubes, much as the telescope makers had done, by placing one lens near the object to be viewed and another near the eye. They discovered they could achieve magnifications far greater than any single lens could provide. The exact inventor remains lost to history, as often happens with practical innovations that emerge gradually from artisan traditions rather than announcing themselves with fanfare. Several Dutch lens grinders likely arrived at similar solutions around the same time, each refining the basic concept. Zacharias Janssen and his father Hans, spectacle makers in Middelburg, are often credited with creating one of the first compound microscopes around 1590. Though the dates remain uncertain and the evidence fragmentary, what we know with greater confidence is that by the 1620s and 1630s, these curious instruments were spreading among natural philosophers across Europe, objects of fascination for those who wondered what lay beyond the threshold of human vision. The early compound microscopes were temperamental instruments. Their lenses, still imperfect in manufacture, produced images plagued by color fringes and distortions. The magnification was modest by later standards, perhaps 20 or 30 times at best. Yet even these limited powers began to reveal astonishing details. The surface of a flea became a landscape of armored plates. The edge of a razor, seemingly smooth to the naked eye, revealed itself as a jagged, mountainous terrain. Seeds showed unexpected patterns and structures. In England, a young man with restless curiosity and remarkable skill in both observation and illustration took up the microscope with unprecedented dedication. Robert Hooke, born on the Isle of Wight in 1635, possessed one of those wide-ranging minds that characterized the early days of scientific investigation. He was an architect, a physicist, an inventor, and a meticulous observer of natural phenomena. In the 1660s, working under the patronage of the newly formed Royal Society of London, Hooke embarked on a systematic examination of the microscopic world. He improved the basic design of the compound microscope, refining the arrangement of lenses and developing better methods of illumination. Candlelight or lamplight, carefully focused, could be directed onto specimens to reveal details that would otherwise remain lost in shadow. Hooke constructed a device with careful attention to stability, for even the slightest tremor would set the magnified image dancing and shimmering beyond recognition. Night after night, Hooke placed specimens beneath his lenses. He examined the point of a needle, mold on leather, the feet of flies, the stinger of a bee. He sliced thin sections of cork and peered at its structure, discovering a pattern of small chambers that reminded him of the cells in a monastery. He called them cells, a name that would endure and eventually transform our understanding of all living things. Though Hooke saw only the empty walls of what had once been living plant tissue. In 1665, Hooke published his observations in a magnificent volume titled Micrographia. This was no dry scientific treatise, but a work of art and wonder. The book contained Hooke's own detailed engravings, large fold-out illustrations that depicted the microscopic world with stunning clarity and beauty. A flea appeared as a fantastic armored creature covered in plates and bristles, its powerful legs clearly designed for leaping. A louse clung to a human hair with tiny claws. The edge of a razor showed gaps and notches that would be chasms at small scales. The compound eye of a fly filled an entire page, its hundreds of facets arranged in geometric precision. Hooke's contemporaries, examining these illustrations by candlelight in their libraries and drawing rooms, found themselves confronted with a revelation. The world contained depths of complexity and structure that no human eye had ever suspected. What appeared simple and smooth at ordinary scales dissolved into elaborate architecture when Magnification pulled back the veil. Micrographia became a sensation, discussed in coffee houses and studied by natural philosophers across Europe. Samuel Pepys, the famous diarist, stayed up until 2 a.m. reading it, calling it the most ingenious book that ever I read in my life. Here was proof that the new optical instruments were not merely extending human vision, but fundamentally transforming it, revealing that familiar objects possessed secret lives at scales too small to perceive unaided. Hooke examined a fragment of petrified wood and saw that its structure perfectly matched ordinary wood, evidence that it had once been living material, now turned to stone. He studied the colors in peacock feathers and discovered they arose not from pigments, but from the microscopic structure of the feathers themselves, though the full explanation of this phenomenon would wait for future understanding of light's wave nature. He observed the crystalline structure of frozen urine and the geometric patterns of snowflakes, each form suggesting underlying principles of organization. The microscope also revealed the living world in motion. In drops of water, Hooke glimpsed tiny creatures moving about, though his compound microscope, still limited by optical imperfections, could not resolve them with perfect clarity. These observations hinted at possibilities that would soon be explored more thoroughly by others with different instruments and sharper eyes. Beyond the specific discoveries, Micrographia established a template for how microscopic observation should be conducted and communicated. Hooke combined careful description with artistic representation, technical improvement with philosophical reflection. He speculated about what his observations meant for understanding nature's fundamental organization, how complexity emerged at every scale of examination. The compound microscope of Hooke's era had limitations that would soon be surpassed by different approaches. The multiple lenses, while providing greater magnification, also multiplied optical imperfections. Each surface introduced distortions. Each thickness of glass absorbed light. Yet these early instruments had accomplished something revolutionary. They had proven that an invisible world existed, waiting to be explored. The textures and structures hidden in the everyday had been brought into view, and natural philosophers now understood that the realm of the very small might hold as many wonders as the telescopic realm of the very large. The age of microscopic revelation had truly begun, and the implications would ripple through natural philosophy for centuries to come. In the quiet town of Delft, along the canals of the Dutch Republic, a most unlikely figure was about to transform humanity's understanding of the living world. While the compound microscopes crafted in learned workshops were revealing remarkable details, a cloth merchant with no formal education would surpass them all through patience, skill, and an almost obsessive dedication to perfection. Antony van Leeuwenhoek was born in 1632 into a family of tradesmen. His youth held no hint of scientific destiny. He learned the draper's trade, travelled briefly to Amsterdam, and returned to Delft to establish himself as a merchant dealing in cloth and notions. His days involved examining fabrics, assessing thread counts, and evaluating the quality of textiles brought to his shop. For this practical purpose, he began using magnifying glasses, simple lenses that allowed him to inspect the fine weave of materials more closely. But something in the experience of magnified vision captured his imagination completely. The small lenses, ground from single pieces of glass, seem to hold secrets that compound microscopes, with their multiple lenses, could not quite reveal. Where others saw a useful tool for practical work, Leeuwenhoek saw an invitation to explore. With no formal training in lens making, he taught himself to grind and polish tiny glass spheres, each no larger than a grain of sand. The technique required extraordinary patience. He would hold fragments of glass in the flame until they formed small globules, then spend hours grinding and polishing them to optical perfection. His methods remained largely secret throughout his life, perhaps from a tradesman's natural inclination to guard professional techniques, or perhaps from simple privacy. He worked alone in his modest home, with no assistants to whom secrets might be passed. The microscopes he created were remarkably simple in construction, yet challenging to use. Unlike the compound microscopes with their tubes and multiple lenses, Leeuwenhoek's instruments consisted of a tiny lens mounted between two metal plates, with a pin or platform to hold the specimen directly before the lens. The user had to hold the device close to the eye, requiring steady hands and considerable patience. The field of view was minute, the lens itself barely visible to the naked eye. Yet these humble instruments achieved magnifications of up to 270 times, far surpassing anything his contemporaries could accomplish. What drove this merchant to spend countless hours perfecting such devices? Perhaps it was the peculiar wonder that comes from seeing what has never been seen before, the quiet thrill of discovery, available even to those outside academic circles. In the 1670s, as he approached middle age, Leeuwenhoek began systematically examining everything he could place before his lenses. He looked at rainwater collected from his roof and found it teeming with tiny creatures, moving and tumbling through the droplet. He examined pepper water, scrapings from his own teeth, blood from his finger. In each sample, he discovered intricate worlds invisible to every human being who had lived before. These were not merely small things made smaller, but entire categories of life that no one had imagined existed. In 1673, Encouraged by a physician friend, Leeuwenhoek wrote his first letter to the Royal Society in London, describing his observations. The letters were composed in Dutch, the only language he knew, later translated for the learned society. Written in a plain, direct style without scientific jargon, they conveyed unmistakable wonder at what he was seeing. His discovery of animalcules, as he called them, tiny creatures swimming in water, opened a conceptual frontier. Here were animals so small that thousands could fit in a single drop, yet each moved with apparent purpose. Each had form and structure. He described them with careful attention. Some were round, others elongated, some moved in spirals, others darted suddenly. He estimated their sizes relative to grains of sand, providing the first measurements of microscopic life. The Royal Society received these reports with fascination mixed with skepticism. Could such tiny creatures truly exist? Were Leeuwenhoek's lenses really capable of such magnification? A delegation was eventually sent to verify his observations, and they confirmed what he had reported. The cloth merchant from Delft was indeed seeing what he claimed. Over the following decades, Leeuwenhoek sent hundreds of letters to the Royal Society, documenting discovery after discovery. He observed red blood cells, describing their shape with precision. He examined the structure of muscle fibers, the compound eyes of insects, the striations in wood and bone. He discovered spermatozoa, those microscopic swimmers whose existence would prove crucial to understanding reproduction. He found bacteria, though he could not have known the significance of these very little animalcules that would later prove central to understanding disease and life itself. What distinguished Leeuwenhoek was not theoretical sophistication, but careful, systematic observation, combined with superior technical skill. He ground perhaps more than 500 lenses during his lifetime, each one an experiment in optical perfection. He developed techniques for preparing specimens, for controlling light, for isolating the phenomena he wished to study. His lack of formal education perhaps freed him from preconceptions, allowing him to report simply what he saw rather than what theory suggested he should see. His contemporaries, using compound microscopes, struggled with optical problems, the multiple lenses introducing distortions and aberrations that blurred fine details. Leeuwenhoek's single lens approach, though difficult to use, avoided these issues. The tiny sphere of glass, perfectly ground, produced images of startling clarity. He never published a formal book, never developed grand theories, never established a school of followers. His legacy existed in those hundreds of letters, written in plain language, describing with methodical care the wonders visible through his lenses. He became famous across Europe, received visits from royalty and scholars, was elected to the Royal Society despite having no university credentials. Yet he remained in Delft, continuing his observations into old age, peering through his tiny lenses at the hidden dimensions of creation. When Leeuwenhoek died in 1723, at the age of 90, he left behind cabinets filled with his microscopes, each one a small masterpiece of lens grinding. The secret of his superior technique died with him, and it would be more than a century before microscope makers could consistently achieve the magnifications he had reached. But the world he revealed remained open. The realm of microscopic life, once glimpsed, could not be forgotten. His animalcules and tiny structures demonstrated that the universe extended in both directions, toward the immense and toward the minute. The same optical principles that allowed telescopes to reveal distant moons now showed that a drop of water contained multitudes, that the invisible teemed with life and complexity. While Antony van Leeuwenhoek peered into the infinitesimally small, observing creatures no human eyes had ever witnessed, another mind across the English Channel was investigating light itself. In a second-floor bedroom of his family's manor house at Woolsthorpe, a young man barely past his 20th year was conducting experiments that would transform our understanding of color, vision, and the very nature of sunlight streaming through the window. The year was 1666, and Isaac Newton had retreated to the countryside from Cambridge, where the university had closed its doors as plague swept through English towns and cities. In this enforced isolation, with time stretching before him and an insatiable curiosity demanding occupation, Newton acquired what he called a prism, a triangular piece of glass that would become one of the most famous experimental tools in the history of science. Prisms were not new. Natural philosophers and curious minds had played with these shaped pieces of glass for years, delighting in the rainbow of colors they produced when sunlight passed through them. But most assumed these colors were somehow created by the glass itself, that the prism modified or stained the pure white light in various ways. It was a reasonable assumption, one that had satisfied observers for generations. Newton thought differently. In the quiet of his chamber, he darkened the room and allowed only a thin beam of sunlight to enter through a small hole in the window shutter. He positioned his prism in this beam's path and watched as it struck the opposite wall, not as a white circle but as an elongated spectrum, a band of colors stretching from deep red through orange, yellow, green, and blue to violet. The sight was beautiful, familiar to anyone who had experimented with prisms, yet Newton looked at it with fresh eyes. The shape of this spectrum puzzled him. If the glass were simply bending the light, why would it elongate into this particular pattern? Why not remain circular? Newton's mathematical mind sought the underlying reason. He began a series of careful experiments, each designed to test a specific question about what he was observing. In one elegant demonstration, he took a second prism and placed it in the path of the colored light, but inverted from the first. If the colors were created by the glass, this second prism should add more modification, perhaps creating new colors or further distorting those already present. Instead, something remarkable occurred. The separated colors recombined into white light again. The second prism undid what the first had done. Newton then tried something even more revealing. He allowed the first prism to spread the light into its spectrum, then used a board with a small hole to isolate just one color, say, a narrow band of green light. He passed this isolated green light through another prism. If the glass created colors by modifying white light, surely it should change this green into other colors. But it did not. The green light bent as it passed through the second prism, but it remained stubbornly green. The same proved true for red, for blue, for every color he isolated. Through these methodical experiments, Newton arrived at a revolutionary conclusion. White light was not pure and simple. Instead, it was a mixture of all the colors. And the prism did not create colors, but merely separated them, bending each by a different amount. Red bent least, violet bent most, and all the colors between arranged themselves in order by how much the glass refracted them. This discovery, which Newton called his experimentum crucis, or crucial experiment, overturned centuries of assumption. Light itself was more complex than anyone had imagined. The rainbow overhead after a storm was not a strange atmospheric phenomenon, but simply nature's own prism. Countless water droplets, each separating sunlight into its component colors for our eyes to perceive. Newton's investigations did not stop with the spectrum. He began to wonder about the nature of light itself. Was it a stream of tiny particles, speeding through space and bouncing off surfaces? This corpuscular theory, as it came to be known, appealed to his mathematical sensibility. It could explain reflection, particles bouncing off mirrors like balls off walls. It could explain refraction, particles speeding up or slowing down as they entered different materials, causing their paths to bend. His work with prisms also led Newton to a practical problem. When he tried to observe the heavens through telescopes, he noticed troubling colored fringes around bright objects. This chromatic aberration, as it was called, occurred because telescope lenses were themselves prisms, bending different colors by different amounts and preventing them from all focusing at the same point. The images appeared blurred and rainbow-edged, limiting what astronomical observers could see. Believing at first that this problem could not be solved with lenses, Newton designed an entirely different kind of telescope. Instead of using a lens to gather and focus light, he employed a curved mirror. Light reflecting off a mirror bounces back regardless of its color. All wavelengths reflect at the same angle. In 1668, Newton constructed a small reflecting telescope, barely 6 inches long, yet it performed as well as much larger lens-based instruments. This compact device, which Newton demonstrated to the Royal Society in London, caused considerable excitement. Here was not merely a theoretical discovery about light and color, but a practical instrument that overcame real limitations. The reflecting telescope design would eventually enable astronomers to build ever larger instruments, since large mirrors were easier to support than large lenses, which could only be held at their edges. Newton's work with light and color would occupy him intermittently throughout his life. He carefully observed the colored patterns that appeared between curved and flat pieces of glass pressed together, delicate concentric rings now called Newton's rings, though he could not fully explain them with his particle theory. He investigated how light behaved at the boundaries between different materials, noting peculiarities that troubled his neat explanations. Yet his fundamental insights about the spectrum endured. White light was composite, not simple. Colors were intrinsic properties of light itself, not qualities added by the materials light passed through. And careful experimentation, not mere philosophical speculation, was the path to understanding nature's secrets. As news of Newton's optical discoveries spread through the small community of natural philosophers in England and across Europe, they sparked both admiration and controversy. Some questioned his conclusions, others his methods. But the experiments could be repeated, the results verified by anyone with a prism and patience. The spectrum appeared for all observers, stretching its bands of color in consistent, reproducible patterns. In the gentle darkness of his room at Woolsthorpe, watching colored light paint patterns on the wall, Newton had opened another hidden world, not the microscopic realm of tiny creatures, but the hidden complexity within something as familiar as sunlight, the light that had bathed humanity since the first dawn, that seemed so simple and pure, contained within itself all the colors the human eye could perceive, waiting only for the right conditions to reveal themselves. As the 17th century drew toward its close, the scientific world found itself contemplating two quite different visions of what light might actually be. Newton's prism experiments had revealed the spectrum, showing that white light could be separated into its rainbow of component colors. But the deeper question remained unanswered, hanging in the air like morning mist. What was light itself, in its fundamental nature? Isaac Newton, already recognized as one of Europe's greatest minds, proposed that light consisted of tiny particles he called corpuscles. These infinitesimal bodies, he suggested, traveled in straight lines from luminous sources, bouncing off mirrors and bending as they passed from one medium to another. The particle theory had an intuitive appeal. After all, light seemed to cast sharp shadows, suggesting it moved in straight rays rather than spreading out the way water ripples do. When you stood before a candle flame, you blocked its light in a definite way, creating darkness behind you. This behavior seemed more consistent with particles traveling in lines than with waves flowing around obstacles. Newton's immense reputation lent considerable weight to this corpuscular theory. His mathematical brilliance had unlocked the secrets of planetary motion and given humanity universal laws of gravitation. When such a mind proposed an explanation for light, the learned world listened with deep attention. The particle model could explain reflection quite elegantly. Imagine tiny spheres bouncing off a smooth surface, like balls rebounding from a wall. It could also account for refraction, the bending of light as it passed from air into water or glass, by suggesting that the particles moved faster or slower in different substances. Yet across the English Channel and the North Sea, a different understanding was taking shape in the mind of Christian Huygens, the brilliant Dutch mathematician, astronomer, and physicist. Huygens had already made his mark on science with improvements to the telescope and the discovery of Saturn's largest moon, Titan. He had invented the pendulum clock, bringing unprecedented precision to the measurement of time. Now, in the quiet hours of contemplation, he developed a theory that light behaved not as a stream of particles, but as waves propagating through space. In his treatise on light, published in 1690, Huygens presented his wave theory with mathematical rigor. He imagined light as a disturbance traveling through an invisible medium that filled all of space, a substance he called the luminiferous ether. Just as sound waves travel through air and water waves move across the surface of a pond, light waves would propagate through this ethereal medium. Each point, touched by a light wave, would become the source of new wavelets, spreading outward in all directions, like the expanding circles created when raindrops strike a still pool. These wavelets would combine and interfere with one another, creating the overall wave front that moved through space. The wave theory possessed its own explanatory power. It could account for refraction, by proposing that light waves traveled at different speeds in different materials, causing the wavefront to bend as it passed from one substance to another, much as ocean waves change direction as they approach a sloping beach. Reflection, too, could be understood through waves bouncing back from a smooth surface, their angle of reflection matching their angle of approach. Here, then, were two competing visions, each proposed by a towering intellect, each capable of explaining the optical phenomena that natural philosophers had observed. The scientific community of the late 17th century found itself in an unusual position. Both theories seemed to work, at least for the most commonly observed behaviors of light. Yet they could not both be true in the same way. Light could not simultaneously be particles and waves, at least not in any way that made intuitive sense to thinkers of that era. The question became, which phenomena might distinguish between these rival theories? Both Newton and Huygens recognized that reflection and refraction alone could not definitively resolve the matter. Each theory could be shaped to accommodate these basic observations. The answer would need to come from more subtle effects, from careful examination of situations where the two theories might predict different outcomes. Newton's particle theory struggled somewhat with a phenomenon that had puzzled natural philosophers for centuries. The colors seen in thin films, such as soap bubbles or the thin layers of air between two pieces of glass pressed together. Newton himself studied these effects extensively, observing the beautiful rings of color that appeared when a curved lens rested on a flat glass plate. These patterns, later named Newton's rings in his honor, showed regular alternations of bright and dark bands. While Newton attempted to explain them through his particle theory by proposing that his corpuscles had properties that created periodic behavior, the explanation grew complex and somewhat forced. Huygens' wave theory, on the other hand, could potentially account for such effects more naturally through the interference of waves, though Huygens himself did not fully develop this explanation. When waves overlap, they can reinforce each other if their peaks align, or cancel each other if a peak meets a trough. This interference could produce the alternating bright and dark bands that thin films displayed. The late 17th century lacked the experimental techniques and instruments needed to decisively test these competing theories. Natural philosophers debated in academies and corresponded in letters, each side marshalling arguments and observations. Newton's authority and the apparent simplicity of the particle model held considerable sway, particularly in England. Many scholars found it easier to imagine tiny bodies flying through space than invisible waves in an undetectable ether. Yet the wave theory persisted, kept alive by Huygens' mathematical treatment and by its ability to explain certain phenomena with elegant economy. The debate was not settled with a single dramatic experiment or observation. Instead, it remained open, a question mark hanging over the nature of light, even as optical instruments grew more sophisticated and useful. This era of competing theories represented something important in the development of science itself. The willingness to entertain multiple explanations, to recognize that observational evidence might not yet be sufficient to decide between them, showed a maturing approach to natural philosophy. Rather than insisting on a single truth handed down by ancient authority, the scientific community of the late 1600s could hold two possibilities in mind simultaneously, waiting for nature to reveal which path led toward deeper understanding. As the century turned and a new age dawned, this question about light's fundamental nature remained unresolved. passed along to the next generation of investigators who would devise new experiments and make new observations. The journey toward understanding would continue, patient and persistent, following wherever the evidence might lead. The question hanging in the air as the 17th century reached its midpoint was not merely what light was made of, but how it moved through the vast darkness of space. Did light travel instantaneously from distant stars to our eyes, appearing the moment we looked upward? Or did it journey across the cosmos at some measurable pace, however swift, taking time to bridge the gulf between celestial bodies and earthly observers? For most of human history, the prevailing assumption had been that light moved infinitely fast. Aristotle had believed this. Kepler had assumed it. The idea seemed almost self-evident, for who had ever perceived any delay between opening their eyes and seeing? When you light a candle across a room, the illumination appears immediate. When the sun breaks over the horizon, we see it rise without apparent postponement. Yet there were doubters. Galileo himself had wondered about this question, and according to accounts, he even attempted an experiment. He and an assistant stationed themselves on hilltops several kilometers apart on a clear night, each holding a shuttered lantern. Galileo would uncover his lantern, and his assistant, upon seeing the flash, would uncover his own. Galileo hoped to measure the time between uncovering his lantern and seeing his assistant's response, subtracting the human reaction time to find light's speed. The attempt yielded nothing conclusive. If light had a speed, it was far too fast for such a simple method to detect. The answer would come not from lanterns on hillsides, but from careful observation of the clockwork heavens, where distances were incomparably greater, and timing could be measured with astronomical precision. In the Danish city of Aarhus in 1644, a boy named Ole Rømer was born into a world increasingly fascinated by the mechanical regularity of celestial motions. He showed early promise in mathematics and was eventually sent to study at the University of Copenhagen, where his abilities caught the attention of the astronomer Rasmus Bartholin. Rømer assisted in making astronomical observations, developing the patience and precision that such work demanded. His talents brought him to Paris in 1672, where the newly established Royal Observatory sought skilled astronomers to carry out an ambitious program of celestial measurements. King Louis XIV had commissioned a magnificent facility, and the Italian astronomer Giovanni Cassini directed its activities. Among their many projects was the careful observation of Jupiter and its family of moons, those wandering points of light that Galileo had first discovered decades earlier. The innermost of Jupiter's large moons, known as Io, orbited the giant planet with remarkable regularity, disappearing into Jupiter's shadow and re-emerging with predictable timing. By 1676, astronomers had been observing these eclipses for years, noting the precise moments when Io vanished behind Jupiter or slipped into its shadow. These observations served as a kind of celestial clock, potentially useful for determining longitude at sea, if the times could be predicted accurately enough. But there was a puzzle. Rømer, meticulously recording the times of Io's eclipses, noticed something peculiar. When Earth in its orbit was moving toward Jupiter, the eclipses occurred slightly earlier than predicted. When Earth was moving away from Jupiter, the eclipses happened slightly later. The discrepancies were small, mere minutes. but they followed a clear pattern that correlated with Earth's changing distance from Jupiter. Other astronomers had noticed these irregularities and proposed various explanations involving Jupiter's orbit or perturbations in Io's motion. But Romer considered a different possibility, one that was both simpler and more profound. Perhaps the timing variations had nothing to do with Jupiter or Io at all. Perhaps they arose because light itself took time to travel across space, and that travel time changed as the distance between Earth and Jupiter changed over the course of Earth's yearly orbit around the Sun. On a late summer day in 1676, Romer presented his findings to the Royal Academy of Sciences in Paris. He explained that when Earth was closest to Jupiter, light from Io had less distance to travel, reaching observers sooner. When Earth was on the opposite side of its orbit, farther from Jupiter, the same light had to traverse an additional distance equal to the diameter of Earth's orbit, causing a delay. Romer calculated that light required about 22 minutes to cross a distance equal to the diameter of Earth's orbit around the Sun. This was an astonishing claim. Light was fast, unimaginably fast by earthly standards, but not instantaneous. It was a traveler, not a magician. The implications rippled outward like rings on a pond. If light had a finite speed, then when we looked at Jupiter, we were seeing it not as it was at that moment, but as it had been minutes earlier when the light began its journey. The stars, vastly more distant, must appear as they were years or even centuries in the past. We lived, in a sense, perpetually in the optical past of the cosmos, seeing a universe of ghosts separated from us, not just by space, but by time itself. Not everyone accepted Romer's conclusion immediately. Cassini, his superior at the Paris Observatory, remained skeptical, preferring explanations that invoked irregularities in Jupiter's system, rather than accepting that light crawled, rather than leapt across space. The Dutch scientist Christiaan Huygens, however, embraced Romer's work enthusiastically. Using Romer's timing measurements and estimates of Earth's orbital diameter, Huygens calculated that light traveled at roughly 220,000 kilometers per second, a figure remarkably close to what we know today. In the decades that followed, other astronomers refined these measurements. James Bradley, the English astronomer royal, discovered in 1728 what he called the aberration of starlight, a slight shift in stars' apparent positions caused by Earth's motion through space combined with light's finite speed. This phenomenon provided independent confirmation of Romer's insight and enabled further refinement of light's velocity. Later still, in the 19th century, experimenters would devise earthbound methods to measure light's speed across distances measured in kilometers rather than astronomical units. French physicist Hippolyte Fizeau used a rotating toothed wheel to chop a light beam into pulses, measuring how quickly it traveled to a distant mirror and back. His colleague Leeuwenhoek improved the technique using rotating mirrors. These terrestrial measurements confirmed what Romer had deduced from watching Jupiter's distant moon. Light moved at a specific, finite, and universal speed. The determination of light speed stands as one of those quiet revolutions in human understanding, less dramatic than the discovery of new worlds through telescopes or invisible creatures through microscopes, but perhaps more philosophically profound. It meant that all optical observation involved not just seeing across space, but seeing backward through time. It suggested that light was a physical phenomenon, subject to physical laws, something that moved through the universe rather than simply existing everywhere at once. And it planted a seed that would grow, centuries later, into our understanding that nothing in the universe can travel faster than light, that its speed represents a cosmic speed limit, woven into the very fabric of space and time. As the 17th century drew toward its close, the study of light had progressed from philosophical speculation about rays and vision to precise measurements of an invisible messenger racing across the solar system. Yet even as some questions found answers, others deepened. The tools for studying light, the lenses and mirrors and prisms, continued to improve, setting the stage for ever more refined investigations into its nature and behavior. With the speed of light now measured and its nature debated between waves and particles, the 18th century turned its attention to a more practical challenge. Knowledge of light's behavior meant little if the instruments designed to capture, to focus it, remained imperfect. The telescopes peering into the heavens and the microscopes revealing hidden worlds were limited not by theory, but by the glass itself. Glass, that ancient material humanity had crafted since Egyptian times, had always been temperamental. Even the finest optical glass of the early 18th century contained impurities, tiny bubbles, streaks of color, variations in density that scattered light unpredictably. When ground into lenses, these flaws became magnified problems. A telescope pointed at Jupiter might reveal its moons, but those moons would swim in halos of distortion. A microscope examining a drop of pond water would show its tiny inhabitants through a veil of chromatic aberration, where different colors of light bent at slightly different angles, creating rainbow fringes around every object. The glassmakers of Venice had long guarded their secrets, but by the 18th century, new centers of glass production emerged across Europe. In England, Germany, and France, craftsmen experimented endlessly with the proportions of their materials. Sand provided the basic structure, but the addition of different substances altered the glass's properties. Lead oxide made glass heavier and more refractive. Potash changed its melting point. Small variations in ingredients or temperature could mean the difference between clarity and cloudiness. The process of creating optical glass required extraordinary patience. Unlike window glass or drinking vessels, where minor imperfections mattered little, lens glass needed near-perfect uniformity. Glassmakers would heat their mixtures in clay crucibles for days, maintaining precise temperatures while the materials melted and fused. Too hot, and bubbles would form. Too cool, and the ingredients wouldn't fully combine. The molten glass had to be stirred carefully to distribute heat evenly, then cooled with agonizing slowness to prevent internal stresses from forming. Once cooled, the glass cylinders or discs would be examined critically. Most pieces were rejected. A bubble the size of a pinhead, invisible in a wine glass, would ruin a telescope lens. Striations, those faint lines where the glass's density varied, were equally disastrous. The acceptable pieces moved on to the lens grinders, but the rejected glass returned to the furnace, melted down to try again. The lens grinders themselves were artists of remarkable skill. Working with abrasives of increasing fineness, they would shape rough glass blanks into precise curves, Early grinders worked by feel and experience, but the 18th century demanded greater precision. Tools were developed to measure curves with accuracy previously unimaginable. A lens maker might spend weeks grinding a single piece, periodically testing its shape against templates, adjusting the curve by fractions of a millimeter. The greatest challenge remained chromatic aberration, that rainbow effect that Newton himself had considered insurmountable. He had turned to reflecting telescopes specifically to avoid it, believing that lenses would always split light into colors. But in 1729, an English gentleman named Chester More Hall discovered something remarkable. Different types of glass bent light by different amounts. What if two lenses, made from different glasses, could be combined to cancel out each other's color distortions? Hall worked quietly on this idea, sending different elements of his design to different opticians so that no one would grasp his complete invention. But secrets have a way of escaping. By the 1750s, the London optician John Dolland had independently arrived at the same solution, crucially, patented it. The achromatic lens, combining crown glass and flint glass in precise configurations, could focus different colors at nearly the same point. The impact was profound. Suddenly, telescopes could be built with lenses rather than mirrors, and those lenses produced images of unprecedented clarity. The planets appeared sharp-edged instead of rainbow-fringed. Stars resolved into points rather than colored blurs. Microscopes, too, benefited, revealing cellular structures with new definition. But creating achromatic lenses demanded even greater precision in glassmaking. Crown glass and flint glass had to be manufactured with exact, consistent properties. A telescope maker might order glass from a supplier, only to find that different batches bent light differently, making it impossible to calculate the correct lens curves. The science of optics had advanced beyond the technology of materials. In Switzerland, a craftsman named Pierre-Louis Guénon became obsessed with perfecting optical glass. For years, he experimented in his workshop, trying different stirring techniques, different cooling rates, different crucible materials. He discovered that stirring molten glass with a clay rod helped distribute its properties more evenly. He developed methods of extremely slow cooling that produced glass of remarkable uniformity. Guénon's glass was revolutionary. Large pieces could be cast with consistent quality, enabling the creation of bigger lenses. Flint glass, particularly difficult to manufacture without defects, emerged from his workshop in unprecedented quality. When word of his achievements spread, Bavaria's Georg von Reichenbach invited him to establish a glass workshop at the Munich Philosophical Instrument Society. There, Guénon's techniques merged with the precision engineering emerging in German workshops. Joseph von Fraunhofer, a young instrument maker of extraordinary talent, worked alongside Guénon, learning the secrets of glass, while contributing his own genius for grinding and polishing. Together, they pushed optical manufacturing to new heights. Fraunhofer developed machines that could grind lenses with mathematical precision, creating curves accurate to tiny fractions. He tested his lenses obsessively, developing methods to measure their quality objectively, rather than relying on the maker's eye alone. The telescopes emerging from this collaboration were magnificent. Fraunhofer's instruments revealed details in distant nebulae that earlier observers had never glimpsed. His microscopes showed biological structures with clarity that amazed natural philosophers. The tools of discovery had caught up with and then surpassed the theories that had guided their creation. By the early 19th century, optical glass and lens making had become both science and art. The empirical trials of centuries had yielded understanding of how different materials behaved, how precise curves affected light's path, how multiple elements could work together to overcome fundamental limitations. The telescopes and microscopes that would enable the next generations of discovery were being perfected in workshops across Europe, each lens a testament to patience, skill, and the steady accumulation of knowledge. As these instruments spread to observatories and laboratories, they awaited the questions that would challenge them. And in England, a physician's son was conducting experiments with light itself, experiments that would reveal something unexpected about its very nature. The opening years of the 19th century found the nature of light still wrapped in considerable mystery. Despite all the advances in lens making and the magnificent instruments that now peered into the heavens and revealed microscopic worlds, the fundamental question remained: what exactly was light? The debate between Newton's particle theory and the wave conception proposed by Huygens had simmered for more than a century, with neither side claiming decisive victory. But in a modest room in London, a physician and natural philosopher named Thomas Young was preparing an experiment so elegant, so beautifully simple, that it would tip the scales dramatically toward understanding light as a wave phenomenon. Young was a man of remarkable breadth. He had studied medicine, practiced as a physician, worked on deciphering Egyptian hieroglyphics, and pursued investigations across numerous scientific domains. His mind moved easily between disciplines, finding connections others missed. In 1801, he turned his attention to a phenomenon that had puzzled natural philosophers: the colourful patterns that sometimes appeared when light passed through narrow openings or around obstacles. These colours couldn't be easily explained by thinking of light as simple particles travelling in straight lines. The experiment Young devised was striking in its simplicity. He allowed sunlight to pass through a small hole, creating a narrow beam. This beam then encountered a thin card or barrier with two narrow slits cut close together. On the other side, a screen waited to receive whatever pattern the light would make after passing through those two openings. If light consisted of particles, as Newton had proposed, one would expect to see two bright bands on the screen, corresponding directly to the two slits. The particles would travel through each opening and hit the screen beyond, creating two distinct illuminated areas. But that was not what appeared on Young's screen. Instead, the light created a series of alternating bright and dark bands, a pattern of stripes spreading across the surface. Where one might expect simple illumination, there was instead an intricate arrangement of light and shadow. The bright bands appeared where light from both slits somehow reinforced itself, while the dark bands emerged where light seemed to cancel itself out. This was the unmistakable signature of interference, a phenomenon well known in the behavior of water waves. When two sets of water waves meet, they interact in predictable ways. Where the crest of one wave meets the crest of another, they combine to create a higher crest. This is constructive interference. Where a crest meets a trough, they cancel each other out, leaving the water momentarily flat. This is destructive interference. Young recognized immediately that his pattern of bright and dark bands showed light behaving in exactly this wave-like manner. Light from one slit was interfering with light from the other, creating regions of brightness where waves aligned, and regions of darkness where they opposed each other. The implications were profound. Young's experiment suggested that light spread out from each slit as waves spread from disturbances in water, overlapping and interacting across space. The precise spacing of the bright and dark bands even allowed Young to calculate the wavelength of light, the distance from one wave crest to the next. These wavelengths proved incredibly small, measured in tiny fractions of a millimeter, which explained why light usually seemed to travel in straight lines. The wave nature only became apparent under carefully arranged conditions where light passed through openings comparable to its wavelength. Young presented his findings to the Royal Society, that venerable institution where natural philosophers gathered to share discoveries. The reception was decidedly mixed. Newton's authority still loomed large over British science decades after his death, and many were reluctant to abandon the particle theory he had championed. Young's ideas met with skepticism and even hostility from some quarters. The mathematical treatment wasn't yet sufficiently developed to convince those who demanded rigorous proof. But across the English Channel, a French engineer and physicist named Augustin Jean Fresnel was independently reaching similar conclusions through his own experiments with light. Fresnel possessed formidable mathematical skills and set about developing a comprehensive mathematical framework for understanding light as waves. Working in the 1810s and 1820s, he created equations that could predict with remarkable precision how light would behave when it encountered obstacles, passed through apertures, or reflected from surfaces. Fresnel's mathematical approach transformed wave theory from an interesting suggestion into a powerful predictive tool. He could calculate the exact patterns that would appear in various optical situations, and his predictions matched experimental observations with impressive accuracy. He explained the phenomenon of diffraction, the slight bending of light around edges and through small openings, as a natural consequence of wave behavior. He showed how the colors appearing in thin films, like soap bubbles or oil on water, resulted from interference between waves reflecting from different surfaces. The French Academy of Sciences, initially skeptical, set up a competition to evaluate theories of light. Fresnel submitted his wave theory, complete with mathematical descriptions. One judge, the physicist Siméon Denis Poisson, tried to disprove Fresnel's theory by showing it led to an absurd prediction. According to Fresnel's equations, if you placed a small disk in a beam of light, there should be a bright spot at the very center of the shadow behind it. This seemed ridiculous. How could there be brightness at the center of a shadow? But when the experiment was actually performed, there was indeed a bright spot exactly where Fresnel's mathematics predicted. The wave theory had passed a stringent test that seemed designed to expose its flaws. As Fresnel's mathematical descriptions grew more sophisticated through the 1820s, more and more optical phenomena found natural explanations within the wave framework. Reflection, refraction, diffraction, interference, polarization. All these diverse behaviors of light could be understood as manifestations of wave motion. The pattern that emerged was too consistent, too mathematically elegant to dismiss. Yet even as the wave theory gained adherence, questions lingered. If light was indeed a wave, what was waving? Water waves needed water. Sound waves needed air. or another medium to propagate through? What medium carried light waves across the vast emptiness of space, bringing us illumination from the sun and distant stars? Natural philosophers began to hypothesize the existence of a mysterious substance they called the luminiferous ether, an invisible medium pervading all space through which light waves supposedly traveled. The story of light was far from complete. The beautiful experiments of Young and the mathematical brilliance of Fresnel had revealed light's wave nature, but deeper mysteries remained. Still, by the 1830s, the optical knowledge accumulated over millennia had reached a remarkable state of sophistication, ready to connect with new discoveries about electricity and magnetism that would eventually reveal even more fundamental truths about the nature of light itself. As the 1840s approached, the science of optics had traveled an extraordinary distance from those first wondering observations of rainbows and firelight in ancient times. The instruments that now graced observatories and laboratories across Europe would have seemed like pure magic to Euclid, or even to Alhazen. Telescopes reached ever deeper into the cosmos, revealing nebulae and star clusters of breathtaking complexity. Microscopes unveiled biological structures so intricate they challenged the imagination. Yet for all this remarkable progress, light itself remained profoundly mysterious. The wave theory had triumphed in explaining many phenomena. Young's interference patterns and Fresnel's mathematical descriptions had convinced most natural philosophers that light must be some form of wave motion. But waves in what? Ocean waves moved through water. Sound waves propagated through air. If light consisted of waves, it surely required some medium through which to travel. This led scientists to propose the existence of a substance they called the luminiferous ether, an invisible material that permeated all of space, even the vacuum between stars. The ether became a source of endless speculation. It needed to possess seemingly contradictory properties. It had to be rigid enough to support the rapid vibrations of light waves, yet also perfectly transparent and offering no resistance to the movement of planets and comets through space. It had to fill every empty corner of the universe, yet remain completely undetectable to any instrument. The more scientists considered this mysterious substance, the stranger it seemed, yet the wave theory of light appeared to demand its existence. Meanwhile, the practical applications of optical knowledge continued to flourish. Photography emerged in the late 1830s, capturing images through the same principles that had fascinated observers of the camera obscura for centuries. Louis Daguerre in France and William Henry Fox Talbot in England developed methods to permanently record the images that lenses projected onto light-sensitive materials. The world could now preserve visual moments in time, a development that would have profound implications for art, science, and society. Optical instruments became increasingly specialized. Astronomers designed ever larger telescopes, grinding mirrors and lenses to exacting specifications. The limitations imposed by chromatic aberration had been largely overcome through clever combinations of different types of glass. Microscope makers refined their instruments to reveal cellular structures in plants and animals. Spectacles became more sophisticated, tailored to correct specific vision problems with greater precision. Yet beneath these practical triumphs, fundamental questions persisted. Scientists had measured light speed with increasing accuracy, finding it to be approximately 300,000 kilometers per second. This almost inconceivable velocity suggested something profound about light's nature, though what exactly remained unclear. Some properties of light seemed to demand a wave explanation, while others appeared more consistent with Newton's old particle theory. The study of polarization presented particularly intriguing puzzles. Certain crystals, like Iceland spar, had the curious property of splitting light rays into two separate beams. When light passed through specific materials or reflected at certain angles, it acquired properties that suggested some kind of directional character. Fresnel and others demonstrated that these polarization effects made sense if light waves oscillated perpendicular to their direction of travel, rather than back and forth along the direction like sound waves. This transverse wave motion added another layer of complexity to understanding light's behavior. As the mid-19th century approached, optical science stood at a curious threshold. It possessed powerful mathematical tools for predicting how light would behave in almost any situation. Engineers could design optical systems with confidence, knowing that lenses and mirrors would perform according to well-established principles. Physicians better understood the eye's structure and function. Artists employed optical principles to create more convincing illusions of depth and illumination. Yet the most basic question of all remained unanswered. What was light? The ancient Greeks had wondered whether it came from the eye or from objects. Alhazen had demonstrated convincingly that it entered the eye from external sources. Newton had imagined particles. Huygens had proposed waves. And the experiments of Young and Fresnel had seemingly settled the matter in favor of waves. But this answer simply pushed the mystery back one step. Waves of what, exactly? How did these waves interact with matter? Why did light sometimes seem to possess particle-like properties? The foundation had been laid for revolutionary discoveries that would come in the latter half of the 19th century and beyond. James Clerk Maxwell would soon demonstrate that light consisted of electromagnetic waves, unifying the studies of electricity, magnetism, and optics in a beautiful mathematical framework. Later still, quantum physics would reveal that light possessed both wave and particle characteristics, resolving the ancient debate by showing that the question itself needed to be reformulated. But none of this diminishes the achievement represented by optical science in the 1840s. Humanity had progressed from wondering about light's nature to harnessing it with precision. The invisible had been made visible through microscopes. The distant had been brought near through telescopes. The fleeting moment could be captured through photography. Mathematical laws described light's behavior with accuracy that enabled reliable predictions and useful technologies. The story of optics demonstrates how human understanding grows through patient observation, careful experimentation, and creative thinking. It shows how practical craftspeople and theoretical philosophers both contributed essential insight. It reveals how progress often comes through questioning established ideas while building upon the solid achievements of earlier generations. As you drift towards sleep, consider how light touches every moment of your waking experience. The words you read, the faces you recognize, the beauty of a sunset or a flower, all depend on light's interaction with your eyes and mind. The instruments that reveal distant galaxies and microscopic life emerged from centuries of human curiosity and ingenuity. The mysteries that remained in the mid-19th century were not failures of optical science, but invitations to future discovery. Each answer had generated new questions. Each solution had revealed deeper layers of complexity. This is the nature of genuine understanding, not a final destination, but an ongoing journey. The optical pioneers we have encountered, from Euclid to Fresnel, would have marveled at what their efforts made possible. They would have recognized, too, that the greatest discoveries often begin with the simplest observations and the courage to ask why. Light itself continues to illuminate both the world around us and the paths of scientific discovery, carrying its mysteries forward into ever deeper understanding. As we bring to a close our journey through the remarkable story of optics, from the earliest wonderings about light and vision to the brilliant inventions of lenses and mirrors that open new worlds to human eyes, we hope these gentle tales of discovery have carried you peacefully through the evening. Thank you for joining us on this quiet exploration of how humanity learned to see the invisible. If these calm adventures have brought you comfort, we'd love to have you with us again. Please like, subscribe, and share your thoughts in the comments below to help other smart sleepers find their way here. And now, as the night deepens and your mind settles into rest, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.